Live on YouTube. Hello, wonderful people of the internet. Welcome back to another episode of Leos Labs. I hope everyone's having a wonderful day. Ekshan, Mage, hey, what's up? Blue, Light, Zero, how are you guys doing? Right, so as of yesterday's stream, I kind of said officially, unofficially that I'm back to streaming and that these streams are going to be co-hosted on YouTube. And so that's what I'm doing right now. We have a live stream on Twitch. We have a live stream on YouTube. The nice thing about the YouTube live stream is that you can kind of go back to previous points in the live stream if you want. So if I explain something, you can go back and rewatch it. You can then catch up on 2x speed. There's a lot of advantages. I also get a free video on demand VOD for people to watch once it's done. And from what I can tell, it doesn't really affect so much my upload schedule or anything like that. Like when I actually put a real upload forward, like that's not a live stream, I think it goes into a different queue so that people are not going to be like, I don't know, they won't see my channel as just live streams. I can also put out like real content, if that makes sense. 1224 Chris NG, what's up? So, traditionally, I wait just a few minutes to let people come into the live stream. People on YouTube might not know this, but I usually do like a quick ramble session, and then we hop into the actual topic at hand. But I don't really have too much to ramble about. I never really know what I'm going to say in these sessions. Why so early? I don't know what time zone you're in, but I'm currently in Barcelona, which puts me in Central European Standard Time. I think we're on Standard Time. What that means is, for me, it's like 1 p.m. and I can stream essentially only while my kid is in daycare from like 1 to 4. My goal is, again, to make these streams like part of my workday so that the majority of my work, at least some part of my work, is done live on stream. This will, of course, hit my efficiency, but I'm a contractor, and so I can just kind of work that into the hours that I'm working, right? So instead of working, like what I do is I say, okay, I've worked like 10 hours today, maybe not 10 hours, I've worked like 5 hours today at 0.5% efficiency, so I only charge for 2.5, depending on how I feel I was going. Most contractors probably wouldn't care, but I do. Kind of late for me, 9 p.m. in Tokyo. Yeah, this is the other issue. There's no time zone I can stream at. There's no time I can stream at. That's going to be okay for like every time zone, right? I used to stream from 5 to 7 a.m. in Japanese Standard Time, but unfortunately that worked okay for people in Europe because it was like 10 p.m. and it worked okay for people in the US. It just didn't work well for anybody, right? Segri, hey, what's up? I am actually American. I'm just living in Europe right now, so I'm living in Barcelona. Just for the record, I've been out of the United States since 2014 when I finished up my... Oh, no, 2010. Yeah, no, 2014. 2014 is when I finished my undergraduate. And so I've been really outside of the US for the past 10 years. There was about a year and a half there where I was inside of the US again. I was working at MIT, and then I ended up kind of living with my parents for a bit during COVID, just because honestly my apartment in Boston was really, really bad. But for the most part, I've been out of the United States for the past 10 years. So I lived in Japan from 2014 to 2019, and then I've been living in Barcelona since 2021-ish, 2022, something like this. So for the past 3 years, I've been here. I will probably remain here for a while. I'm not entirely sure how long, but I don't know. It just depends on my wife's job and stuff like that. How are you finding Barcelona and Spain? Honestly, I like Barcelona. When I was growing up, I did not consider myself to be a city boy. You know, like I always felt like city people were like just a different breed of people, and I was not one of them, you know? But since moving to Boston and living here, to be honest, I'm a big fan. Maybe it's just European style cities that I enjoy, but I'm a really, really big fan of cities with good public transportation. I enjoyed Osaka. I enjoyed Tokyo. Okinawa was great for me because it's kind of like the middle ground between what you'd expect from an American, like an American-esque suburb type situation, and what you would expect from Japanese, like kind of technical public transportation, all this kind of stuff. Us Europeans going to be happy? Yeah, I mean, you're going to be able to watch me during this time zone, which will hopefully be watchable for a lot of people. España, yes, España. So the truth is, I don't want to get into the politics of it, but this particular location where I'm at in Barcelona, Spain, kind of, I mean, they're Spanish. Everyone acknowledges that they are in Spain, but there is a big movement to create an independent Catalonia, so that Barcelona is kind of separate. This area, this region of Spain is a separate country. There's a lot of reasons for this, dealing with like social divides between Catalonia and the rest of Spain, and I don't really want to get into that, but I'm saying that if you were to come here and you were to call people here Spanish, they might feel a little bit miffed depending on who you're talking to, right? And like Sagiri said, it will never happen. It's just kind of like, well, I don't know. Like, this is stuff I don't really want to talk about so much, and maybe I should not have brought it up on stream. For me personally, as someone who is from outside of Europe, coming into Europe, I really like this area. I think it's really nice. I like the people around me. I'm enjoying my time being here. People are very friendly, even though I don't speak as much Spanish as I should, and my Catalan is almost non-existent. I'm able to get around. Can we get into Catalan numbers? That might be something to talk about in the bit, because honestly, I don't remember what they are at all. I don't remember, like, what... Yeah, I should remember them, but I don't, right? Okay, speaking of things that I should remember and I don't, let's go ahead and start talking about the topic of today's stream, which is quantum computing. Whoa, hey, quantum computing, let's go! Okay, I'm gonna be honest, and I'm gonna just start the stream off with my honest opinions about quantum computing right now. Kind of thorny topic that's steering our politics a lot. I better stay out of it. Yeah, okay. Oh, Catalan numbers. I didn't realize they were so thorny, to be honest. I thought it was more just a math thing, but maybe it is a political thing. I'm not entirely sure. Regardless, let's talk about quantum computing. So I have kind of like weird opinions when it comes to quantum computing, and they're very similar opinions to what I have for, I just realized something. I need to change my my updates on Twitch. It needs to say quantum analog quantum computing, and then we need to say here and say failed to set the correct. Sorry about that. Okay, so now it's the actual correct title on Twitch. Done. My bad. I've just been reading about D-Wave because it was on the front page of Hacker News. Their tech seems like it is based on marketing nonsense rather than being actual proper quantum computing. Right. This is my core issue I have with quantum computing as it is right now. I have a very similar opinion when it comes to machine learning. Also, you don't have to be sorry for being late. There's a reason I'm streaming on YouTube. I know people can't watch like as it's going live, and so I'm more than happy to have people come in the VOD, make comments on the YouTube video after it's out. In fact, I'm quite happy with the number of comments we got from the last video. I know it was just like a quick update video. I said, yo, all this kind of stuff. But I'm really happy with people. They were suggesting things that we could talk about. A lot of it was AI related because I think that's like the hot tech topic right now. But obviously any topic, I think as we start like doing more of these streams, I think people will start to recognize kind of what things are kind of maybe good to talk about and what aren't, you know? I'm just waiting to where we can factor bigger numbers. Yeah, so this is... Let's talk about quantum computing. Okay, I feel like I'm going to open up Zonal PP and let's just kind of chat for a bit about vibes. I think a lot of people don't talk about vibes enough, and I think vibes are really important to talk about. So let's open up Zonal PP and let's just talk. So quantum computing. Okay, hello there, my pen. 1 second, I am failing miserably and you guys can't see what I'm doing. So quantum computing vibes. All right. I think what I actually want to start with is something different. I want to talk about machine learning vibes. Because I feel like somehow they're not correlated. They're not really related unless you're doing quantum machine learning. But I feel like the vibes are quite similar. So here's the thing. Machine learning, as a concept, as an idea, really does push the boundary of what we can do. There's a whole bunch of really interesting things that are within the realm of machine learning, right? And it's such a big area, right? That there's so many different things you could mean when you say machine learning. You could mean large language models, like, you know, anything from OpenAI. We could be talking about ChatGPT, this type of stuff, right? And for the most part, when you say machine learning nowadays, you're probably talking about large language models, but that wasn't necessarily always true. You could have also been talking about optimization-esque things, esque techniques, which I would call optimal control, but some people really do put gradient descent. They say gradient descent is a form of machine learning, and I can't really argue with that, right? Because gradient descent is one of the like key integral elements to a machine learning model. So if you say you're doing something with gradient descent, you could maybe, you know, wrap the machine learning label around it. Then there's also like online learning methods. What are the names of these guys? Reinforcement learning. And then there's just general AI, right? Like, just like, we'll talk about AI, like, you know, when we're talking about, like, for video games or something like this. Like you could say, like, they used a little bit of machine learning in, for example, Super Smash Brothers with the amiibo or something like this. Like, just general, we'll just say video game AI, and everyone knows what we're talking about. Oh yeah, Bayes. Yeah, this is also great. Yeah, Bayes theorem. And stuff like this. There's just a whole bunch of things that people could mean when they say machine learning, right? And so, and again, this is exactly what Rustican is saying up here. People using machine learning AI when when an SQL query or two will suffice. Yeah, this is, I think, exactly my problem with a lot of these machine learning guys. Like they take the machine learning label because it's a hot topic, and then they just stretch it over kind of everything. They're like, hey, by the way, gradient descent is AI, and yeah, I guess. And so it's really difficult to know what people mean when they say machine learning, right? So we'll go to the quantum. I'll go ahead and read this. I feel like quantum computing is like AI. Let me explain. In the past, before it blew up and was niche, much less niche than quantum computers. People know what AI is and always wanted to be into AI. Now, quantum computing is very niche, and people don't know much about it, me included, and it's waiting to blow up and maybe one day go mainstream. I think that in a similar way, I understand where you're coming from, and we'll talk about that in a bit. Policy learning, another thing. Actually, to be honest, I don't know much about policy learning. What does this mean? Right? Well, what does it mean exactly? Another thing I see is ML for initial guesses for making existing optimization techniques to start on a better first guess. Yeah, this would be heuristic. I don't know how to put heuristic removal, replacement. Basically, anything that you have a heuristic for. You can just stick an ML model in there. So anything we don't have a good analytical guess for, you can basically use a machine learning model for, and it's probably going to do okay, right? Because we didn't really have a good idea of why we needed this particular, I don't know, potential or something beforehand. So sticking in a machine learning model for that makes a lot of sense. Let me go ahead and catch up on YouTube chat over here. I'm just waiting to where we can factor bigger numbers. Yep, that's something we can talk about for quantum computing. Latest I read was like 20 bits or something. What about naive Bayes? Yep, if you're updating values in a matrix, it's machine learning. Yeah, but that's the thing, right? Some people genuinely feel like that, you know? Glad you're back. Hey, thanks for coming by, you know? Control system. So anyway, my point is, here's my point. Before talking about quantum computing vibe, let's talk about another hot topic, which is machine learning. And the fact is that it's so hypey nowadays. It's so hypey that when people are talking about machine learning, they could mean any number of things, and it's not very clear what they're doing. And so when people start talking about machine learning, it's very difficult, even among experts, to come together and have a conclusive argument or discussion about anything, right? Everything ends up turning into this kind of hype and buzzword soup. And again, this even happens among expert people, right? And one other thing I really dislike about machine learning is it kind of turned my archive viewing into I don't know, nowadays, every time I go in the archive, not even every other paper, I'd say 80% of the papers in areas that I used to really enjoy reading are now about AI, right? Or you'll be reading a paper and all of a sudden AI pops up and it's like, well, I didn't want to read about AI now. And so in a sense, my core issue with AI and machine learning is that it's not necessarily that these are bad tools. I think that they do have their use. It's just that when it comes down to it, there's so much hype around them, it's very, very difficult to have an honest discussion, right? And I'm not saying quantum computing is exact there. I think, Zagiri, what you said earlier is exactly right. I think we're kind of on the cusp of having another hypey thing in quantum computing, right? And I want to talk about that a bit. Literally saw an AI job, spoilers, it was dumb, Excel job. I'm not joking. Yeah, this is it. I think everyone just kind of slaps AI on what they want, what they're doing. They just say, yo, this job, which has nothing to do with AI, it could be an SQL database thing. They're like, yo, this is now AI. It's that's not AI though, right? And everyone has to know that's not AI. And you also see with all the hype around ChatGPT and stuff, you just see people who are they're just unnecessarily using ChatGPT without really thinking about why they should be using it, right? They're basically using ChatGPT as they would use Stack Overflow as basically an excuse not to learn something. And anytime people use an AI model to replace actual learning, of course I'm going to be upset because I enjoy learning, right? This is a key integral thing that is fun for me to do, right? Lots of jobs in the field are preparing for ETL for ingestion by the models. Okay, this might be me not understanding. What is ETL? It's like internet in 2000s, overly hyped, then the bubble burst, but underlying tech was really solid. I think there's something like this. I think that will probably be the case. I think in 10 years, when we start talking about machine learning, we'll see it as what it is, a very useful tool. And people will stop talking about all of these general AI stuff. Right now, my understanding is there is no real way to take the currently existing AI models and turn them into a general purpose AI that actually can think and reason about things legitimately. again, I might not be saying the right words, but I think people understand what I'm talking about. Still remember my classmate's paper is about using AI to read sensor numbers. So there are actually uses for AI, and I'm not going to sit here and say there aren't. Like, for example, computer vision, completely super helpful, right? Back at OIST, there were these people, this group that was using computer vision in order to identify like where the queen is in a hive of bees, which is actually very difficult to do. But it's very important to figure out where that queen is so that you can tell what the bees are going to do, how they're going to act, and why they act in that way, right? This is something that was relatively easy to do for an AI, but relatively difficult to do for a human, right? And there are certain situations where AI flat out is better than like a random grad student, you know what I mean? Anyway, we can keep talking about this for a bit more, but I do want to actually talk about today's main topic, which is quantum computing, and talk about where it is right now. And where I believe it to be, right? So remember, if you're watching this in the VOD, like after the fact, after this stream is done, I don't know everything, right? I'm just talking about what I think I know. And I'm really, expecting and hoping that people in the comment section of the YouTube video, people in chat here, just correct me when I have a bad take. Like if I say something stupid, or if I say something that's clearly coming from a place of ignorance, I'm asking that you guys tell me exactly what I said and why it was wrong, and then we can go from there. So, what do we have here? Extract, transform, load, so processing, scrape web pages. Sure, yeah, this is all totally fair. This is stuff that I don't think a human could reasonably do. Control systems. Quantum computing is cool, but the progress not only depends on us software and computer people, engineers and physicists will play a big part. Also, an AI that can think for itself will take a long time, actually, and I'm not even sure it will happen in my lifetime. I don't think it's even theoretically possible, but that's another stream. I would prefer AI to do my household chores, like doing my laundry or cooking dinner. To be fair, I like cooking, and actually there's like some joy to be had in cleaning, like doing laundry and stuff like this. So I don't necessarily want an AI to take that over. I kind of feel like there's something to be said of like doing very simple tasks and completing those simple tasks, especially if you're in like a bit of a mental funk. Just literally like picking up clothes from, your floor can just be enough to get that momentum started and get your day going from a bad day to a good day, So I don't necessarily think that AI should be taking all of our jobs from us, like all these even menial jobs. But there are certain things that undoubtedly AI can do a better job than we can. For example, translation. I use AI all the time to translate between Spanish, Catalan, English, Japanese, whatever I need, And I think expecting me as a foreigner to walk into a country and to be able to have legitimate conversations with people here while I'm learning the language. I mean, it's just much easier if I have Google Translate, So I am more than willing to see AI as a tool. However, we're going to table a lot more of these discussions, right? We're going to be having these discussions in the near future. And if you want to talk about more of this, either mention it here on the Twitch chat or put it in the comment section on the YouTube video for me to just put into the paper pile on Discord, or just mention it in the paper pile on Discord. There are already a lot of people who want to talk about AI as it pertains to policy, like what AI policy should be and why it should be that way. There were people who wanted to talk about AI in terms of GPU and the tech used to actually run AI models. There were people who wanted to talk about AI just in terms of random things, like maybe even cellular autonomy, which is not AI, but is similar. There's a lot of stuff that we could talk about here, and we will talk about it, but they're for future streams. Today's not about AI. I just wanted to start there to kind of explain where I'm coming from when I start talking about quantum computing. I'm coming from a very similar place in that I feel like there are a lot of these initiatives all over the place with quantum computing, but none of them have really taken off to the point where I feel like it's I don't know, it's not like in scam territory, but there's a lot of hype and a lot of buzzwords, and it's very hard to wade through those. That's what I want to say. Current quantum computers only do quantum annealing, so aren't even capable of doing stuff they are hyped to do one day. Right, so this is another thing, right? So let's actually now start talking about quantum computing in reality, right? So the fact is, and this is just, I'm going to be honest here, and I have to start where I am, right? My PhD was in quantum. Right, my PhD was in using GPUs to perform quantum simulations, right? Now, when I say that, what I mean is I did not do quantum information as it is classically trained, right? I took a class in quantum information. I know a lot about how it works, but I've forgotten most of that class, I did a lot of quantum computing simulations. In fact, I was one of the first people that I know of to do quantum circuit simulations in Julia. And I did that live on stream, like literally 8 years ago, right? I'm not going to sit here and pretend that I don't know anything, but I would argue that I don't know that much, right? I'm not going to, you know, like, I have been in adjacent areas a lot throughout my professional career, but I can hardly be called an expert in quantum computing, right? Now, this is kind of where there's this effect. It's called the Dunning-Kruger effect, right? And I feel like this happens to a lot of people who are like, who think they know about quantum computing or any technical topic, right? So the Dunning-Kruger effect essentially says the following, right? There is this plot for people's like, how do I put it? Their belief that they understand something, their energy, their arrogance, their I guess the belief that they understand something versus their actual understanding, right? So we'll put belief over here. And guys, give me the actual names. Did I even spell belief right? I think it's E before I. No, I before E, right? Let's just say perceived knowledge versus actual knowledge. So we'll put perceived knowledge here. And we'll put actual knowledge here. Okay, so this is saying, again, called the Dunning-Kruger effect, where if you don't know anything, right, you think you don't know anything, so you're down here. But as you start to get a little bit of information, right, all of a sudden you feel like you know everything. And then as you start to learn more and more, it quickly drops off. And then it slowly comes back up like this, right? So this is something called the Dunning-Kruger effect, right? So basically, if you don't know anything, right, you're down here. You know you don't know anything. As you start to learn just a little bit, right, all of a sudden you feel like you know everything and you're like, man, I understand quantum computing, I understand AI, I understand whatever it is. You feel like you understand it really well, right? And then you quickly realize, actually, no, you don't. As you start learning more and more, you get into this trough of like despair where you realize, actually, I don't know anything. And then as you start learning more and more, you start to move up here to where you do realize, okay, I'm now maybe a classically trained expert in this area, right? So in terms of where I'm at for quantum computing, I would argue I'm maybe, if you were to objectively measure me, I'm probably exactly here at the bottom of this trough, right? I might be slowly crawling myself up, but even though I have a PhD in quantum systems, this is quite different than quantum information, right? And so I recognize where I'm at, and I don't want to say anything foolish. So I will now start to say foolish things, like things that my current understanding of this area, but keep in mind, I'm here to learn, right? And so when I say something stupid, I would like you guys to correct me and explain what the thing is that I said that was stupid. I just like quantum computing because people think I'm good at it when my job name contains the word quantum. Yeah, that's exactly my problem as well. Like, I did a PhD in quantum systems simulations. So I say, yeah, I guess I know quantum. I do. I understand Bose-Einstein condensation. I understand superfluids. I understand this stuff. I know Hamiltonians. I know, probability density functions. I get this. But then they're like, oh, but how does Shor's algorithm work? I'm like, well, I mean, I did a simulation of Shor's algorithm when I was in a PhD, but it's not there. I'm not a quantum info guy. I'm a quantum chemist, so I'm about as far removed from information theory as you can get in the field. That's fair. I mean, but also like, I feel what's bizarre to me is that 5 years ago, if you said quantum chemistry, like everyone, in fact, if you said quantum, people would probably assume you're a chemist more than a physicist, right? Maybe not exactly, but there's certainly a group of people where when you say quantum, people assume chemistry because they have like, I don't know, these like a number of different models here. And so it's weird to me that nowadays when people say quantum, they're assuming info, right? It's such a strange shift to me as someone who went through undergraduate and started their research taking quantum chemistry classes and stuff like this, As a matter of fact, it applies for almost everything. Yeah, so this Dunning-Kruger, it affects everywhere. It's not just like quantum, it's also like every other field as well. Okay, so let's talk about what I know about quantum computing. So here's what I know, and here's kind of what I feel. So let's go here. One, there's this thing called like universal quantum computer. All right, let's start there. A universal quantum computer. Okay, what does this mean? It means that all of your qubits are able to interact with all of your other qubits, okay? Now, what is a qubit? A qubit is a quantum bit that has the ability to be in either an up state or a down state, right? So very similar to how you have an on and off in like a classical bit situation. Now, there are a lot of weird quantum effects that happen to qubits that don't happen to classical bits. So let's talk about those quantum effects. Quantum effects. So you have, for example, entanglement. What this means is if you have two bits and they're entangled, let's say both are upspin or they're one's up and one's down, you can push these qubits to be as far away as possible, right? Like they could be light years away, right? And if you measure one qubit to be up, right, then the other qubit has to be down, right? What it says is that these bits are correlated together. So if you have, if you measure one to be positive, the other one has to be the corresponding, has to correspond to that measurement, right? And this goes into the fact that measurement in a quantum system, rather a quantum information system, is like one of these, like, it's called an arrow of time. So arrows of time are these like events in physics that when you go through this event, it must signify a movement forward in time. That sounds really weird, right? Because when you think about like the throwing of a ball, right, via a physics equation, you expect the ball to like drop and then bounce and then do whatever the ball would do, right? Like you're naturally thinking that the ball must move forward in time. But when you think about kinematics, like all that equation is a method to explain how objects do move forward in time, right? Or do move with time. But it doesn't necessarily mean that, time has to move forward, right? Like you could also solve that equation with time going backwards. And for the mathematics and the physics, it doesn't really change anything, right? I'm not doing the best job explaining this, but the point is that an arrow of time is something like the second law of thermodynamics. So if you have hot water and cold water and you mix them together, it's going to create lukewarm water, right? What that means is that this spreading of temperature or the spreading of these different microstates and macrostates, essentially the movement of the particles in a system, have a natural way in which they evolve, right? And there's basically no situation you could imagine where you have a lukewarm body of water and all of a sudden the cold water is all separated on one side and the hot water is all separated on another. It's just not going to happen, right? This is one of those things that it's just so unusual and so unlikely that it's considered to be an arrow of time. It's considered to be that, this mutual diffusion of temperature, hot and cold mixing together. It's just, that is always going to happen, right? And so the quantum measurement is another one of these things where it signifies that there's no way to go back, right? You can't go back after a measurement happens, right? Similar to how you can't go back after the temperatures have mixed, you can't go back after doing a measurement. And so before you do that measurement, these quantum states could be anything. They could be up, down, they could be left, right. I mean, they really could be anything on what's known as a Bloch sphere. But after that measurement happens, then the entanglement kind of pops off and you know that these bits are now aligned in this way, right? And so one of the interesting things about quantum bits as opposed to classical bits is you never know what they are until this measurement event. Anyway, this is a lot of rambling about stuff that I really don't know that much about. But what I will say is that this entanglement feature, right, in principle, in a universal quantum computer, could happen across any bit in the system, right? So bit 1 could be entangled with bit 2, 3, 4, 10, whatever it happens to be, right? But we have no, at least that I'm aware of, we have no experimental system that allows for the universal quantum computer to exist. Right now, all I know that we have are nearest neighbor quantum systems, which means that the algorithms that we can implement on a quantum computer are limited to those that can be implemented with nearest neighbor approaches. Now, what algorithms can be implemented with nearest neighbor entanglement? I think most of them can, but I'm not entirely sure what that means. When it comes to quantum computing, there's really only two things. Really only one thing that quantum computing can do better than a classical system, and that has to do with prime factorization and Shor's algorithm, right? So you hear all the time people are saying that quantum computing is the next big thing. It's gonna it's gonna be the next big thing in quantum in computing. It's going to revolutionize computing as we know it. But when you actually look at the algorithms that can be implemented on a quantum computer that cannot be implemented on a classical computer, it really is truly just prime factorization. That's the main thing that we're focusing on. And you might be wondering, why do we care about prime factorization? It's because when it comes down to encryption, that is the way in which people keep secrets, a lot of these secrets are behind encryption or ciphers that rely on the fact that prime factorization is a difficult problem to solve, right? And because prime factorization is such a difficult problem to solve, we've used that concept in almost all of our encryption schemes, right? And so if we have a quantum computer, in principle, if this quantum computer is really good at factorization, then we can break all the ciphers, right? That's the thing, right? Now, what does this mean? This means when quantum computers come online, we, in the classical computing space, better have a way to better have quantum computing resistant algorithms for this technology, right? That's kind of what we're talking about, right? I only use ROT13 encryption. Suck at factorization. That's actually a really funny comment. We need to talk about encryption in different schemes. But my point here is that when it comes to quantum computing, there are two different directions. One is just to keep going with quantum computing and to start focusing on quantum cryptography as a way to create, like, maybe you could imagine like a quantum drive that's attached to your hard drive that just does all of your encryption and decryption for you. Maybe this is a way in which it is used in the future. It's difficult for me to see how we are actually going to be using quantum computing in the next 10 years or 20 years for that matter. I don't know, right? But when we're talking about the usage of quantum computing, no doubt it's going to have a huge impact on the cryptography space. We know this, right? Let me go ahead and catch up on chat. I read somewhere that some of these quantum computers need a constant supply of liquid nitrogen to cool the CPUs enough. How feasible would it be for this to be, for mass production? Yeah, this is a good question. So when it comes to the experimental quantum computers, like things that are actually doing quantum computing now, like physical devices, I think most of them need to be near 0 Kelvin, which is very difficult to do. I don't know if anyone's had the experience of working with low temperature cold atomic systems, but it's very, very hard to maintain that temperature for long, right? You need to essentially, there's 100 different ways to do it, but essentially what you have to do is you've got to first of all cool it down with I don't know, some sort of laser cooling or something like this. There's 100 different ways to do that. And then once you cooled it down sufficiently, you then have to essentially create a vacuum around the product, around the thing that you're trying to make super cooled, because that vacuum will take all the particles out. And again, particle movement indicates temperature. So essentially, not only do you have to cool things down, you also have to have it in like this super pure vacuum. It's very difficult to do. Now, there are people who are working on room temperature superconducting bits and qubits and stuff like that. And those people, if they are successful, will allow for quantum computing to be used in a traditional way. But right now, as it's set, it's very difficult for me to say that quantum computing is the next big wave because we have all of these big experimental things that we have to work past. I see the chat down here. Let me go ahead and catch up on all this. Don't you think that quantum physics is not really a physics theory, but a mathematical one? It says we don't know why something moves in a specific direction, so let's approximate it with probabilities. Physical ones would try to explain the movement. Hey, actually, this is a good question. There are a whole bunch of quantum physics theories that are not actually quantum, right? Oh gosh, what is it? It's there's a very famous theory. What is it called? I can't remember the name of it. But yeah, there are people who try to describe quantum physics without using, I guess, traditionally quantum ideas, right? And when you ask yourself, what really is quantum? It's very difficult, right? This is a big problem people have when they're entering quantum physics as a thing to study, right? Because the interpretation of quantum mechanics is not incredibly clear. It's not like this is also its own field of study. What we do know is that you can use quantum effects to do a lot of engineering, and that engineering, when it's done, ends up creating useful products, right? And so in a sense, most quantum physicists acknowledge that, yeah, maybe we don't fully understand the interpretation of these quantum systems, but that interpretation doesn't quite matter so much because we can actually use it for real world products, and that does matter in a bit more. Are you in a vacuum? Because you're super cool. That is by far the best pickup line I've ever heard in my life. That is amazing. It will work on precisely one person. Like, you can keep using that pickup line again and again and again, and you will find only one person who will understand that joke. But if they do, man, they will love you for all eternity. Like, that is it. That is such a good pickup line. There are also Grover's algorithm, right, versus N for unstructured search, and quantum Fourier transform. You're right. There are these other things. I was going to mention Grover's, but the reason I didn't is because there has been, maybe back when I was studying this to begin with, maybe this has changed recently. It wasn't clear to me that Grover's actually was better in terms of big O notation. It wasn't actually better from a complexity standpoint, but you might be right. Quantum Fourier transform, yeah, QFT, I should have mentioned QFT as well. Let's just throw that down there. QFT, I certainly should have mentioned that. That's a big one. I don't actually know, VQE, yep, know about this as well. But the one I don't know is the quantum approximation optimization algorithm. That one I want to look into. Good. Wolfram's multi-way graph is an interesting quantum model. Yeah, I don't want to talk. So the problem with physicists is some of them are super into the theory of physics. They're really, really into like trying to find an equation for everything. You've got like string theorists, you've got all these people who are like really, really into this. And then you've got people like me who I don't care so much about, like, I figure in the next 1,000, 10,000, 100,000 years, we might have, you know, theories for everything, and that's fine. But I am more interested in like theories for things that we can tangibly work with, like things that are on our desk that we can like actually experimentally validate right now. And so sure, theories of everything are interesting. And I suppose if you really want to make a name for yourself, discovering the theory of everything is going to be like a monumental shift. And like people in 1,000 years are definitely going to remember your name. But to be honest, I am of the opinion that as we are right now, it's very difficult to, it's arrogant, I would say, to assume that the tools we have right now are refined enough to discover said theory. That's what I would say. Let me go ahead and catch up on YouTube chat, then I'll go back up to Twitch chat. I prefer AI to do, okay, discrete logarithm. I don't remember what that was related to. I'm so sorry, I missed like 10 minutes of chat. There's experiments making quantum internet, probably less of a hard drive and more of a quantum network bridge. This is actually something I don't understand about quantum physics or quantum information. Like how does quantum info, how do you store quantum data? I guess is my question. I know it's in qubits, but like physically, what does that mean, right? Like, and that does differ depending on whether you're using a cold atomic system for your qubits or you're using, you know, I don't know, whatever Google and IBM do. It's like 100 different things here, right? I think for Shor's algorithm, there's a famous one for integer factorization, and then other ones for less famous crypto systems, right? I think you're right about that. There's recent breakthrough using shapes to calculate amplitude without path integral. Oh, we're talking about for string theory. Actually, to be honest, my knowledge of string theory is non-existent. In fact, if you start asking me questions about like, I mean, even like general relativity things, I'm not really into these types of things. Kind of the more like useful the information becomes, well, not useful, but more like, how do I put this? When you start talking about things way beyond what I can hold in my hand, I get a little bit sketched a bit. Like, you know, like when you start talking about even dark matter and stuff, I get a little sketched a bit. I feel like, yes, I totally understand why dark matter exists as a way to solve certain theoretical constraints that we have with our current understanding of the world around us. But it's weird when you think of dark matter as an actual thing that exists as opposed to a way to make the math work out. You know what I mean? And that's where you kind of lose me. I am not yet of the opinion that like, I'm of the opinion that we're missing some mathematical tools, not that there's like a physical object that is dark matter out there, right? But maybe I'm wrong. Maybe I don't understand, you know, the world enough. And that's also totally fair. And that opinion I just shared was one of ignorance, right? I don't understand how this works. And because I don't understand how this works, I'm saying stuff that I don't know. So if what I just said about dark matter makes you upset, tell me why it makes you upset and like teach me, because I don't know, right? I don't think Wolfram's theory can already predict the established theories, so it might be nonsense. Yeah, since you are, may I ask a question that's off topic, related to CS, it's for myself. Feel free to ask the question and I will tell you whether I can or cannot answer it. The truth is that a lot of people here in chat have like a lot of experience that I don't have, and a lot of times I can't fully answer those questions. So let's keep going, talking about quantum computing vibes, and then we'll start talking about what I actually want to talk about today. So we already talked about how universal quantum computers currently do not exist, that there's a whole bunch of quantum effects that we can take advantage of, entanglement, the measurement, but there's other things as well that I didn't mention. There's methods for like quantum teleportation, which is a process by which you can send information you know, faster than the speed of light from one point to another using entanglement and a lot of these other features. The disadvantage or the weird thing about these types of effects is that like, even if you can send information or rather, how do I put this? If you have two qubits that are entangled, right? Let's say qubit A and qubit B, right? And so qubit A is always up and qubit B is always down, right? But you don't know because it's a qubit. It could be either up or down. When you measure A, right, to be up, then this one has to be down, right? So after this measurement has happened on this side, this measurement on this side has now happened, right? So that bit is definitely a down state. The problem is you can't tell the person standing here, right? That this will be a downstate, right? Because you're all the way over here, right? And so the only way you can send that information across and you can tell the other person that this is a downstate is via a classical communication channel. And that classical communication channel can only happen at the speed of light. And so even though technically we have faster than light communications, it's not faster than light because the ability to send the actual information that the person needs still has to be sent via a classical channel. Does this make sense? Like there's all of these weird caveats when it comes to quantumness that make it so it's like, it's impressive. Like there's some interesting concepts here. Like basically this is how I feel with the whole, like everything when it comes to quantum information feels this way. Like, okay, there's something cool happening, but we're not smart enough to figure out how to actually take advantage of this cool thing that's happening, right? And that's how it really feels to me when it comes to basically anything quantum. It always feels like, yeah, there is something really, really cool happening here, but I don't really know how we're taking advantage of it, Let's see. I went back to school for CS. Do you have any advice in regards to doing well and learning and not getting stuck? I thought I asked since you were into academics for a long time. Yeah, so I'm still into academics. I love reading papers. And I think when it comes to doing well in school, I have maybe a hot take. My hot take is that if you're going into school with the intention of just doing well in school, I think you're going in school for the wrong reason. And I'm not saying that you in particular, Siguria, are going to school for the wrong reason. Rather, the point of a class, the point of any type of learning exercise is not to learn like whatever the topic is. Like let's say you're in an optics class. Okay, you're not here to learn optics. What you're there to learn are essential tools to help you out with the rest of your career, right? And so don't worry about getting an A in the class, is what I would say. Yeah, you might need that if you are going to a job afterwards and they care a lot about your CV for whatever reason. But I would argue those aren't the jobs you want anyway. What you want is to go into the class and try to identify what things you actually want to learn and what things are going to help you with your future career, right? So for example, if you as an individual really want to be, you want to do machine learning in the future, like it's a hot topic, everybody wants to do this. When you go into classes, relate everything you're doing in the class to how it will help you eventually when you start doing these large machine learning models. Like, how does the thing help you, right? And in doing so, you'll find that you accelerate the learning of those specific areas that are useful. But because you have a natural interest in the class due to relating it to things that you know and you want to do in the future, you will also find that the other areas increase as well, right? And so essentially what I always say is that when you want to learn, define a goal in your head of like where you want to be in 10 years and do everything you can to get there, right? And if you're feeling discouraged, what you should do is you should always look at who you were 6 months ago, right? And compare yourself to that person, right? And see if you've actively made advancements, if you've learned more, if you've grown as a person in those 6 months, right? And so this is kind of the way I see it, have some vague goal of where you want to be in the future. And then in the background, keep in mind where you were and kind of plot your trajectory to say, okay, look, I need to get there. Sure, maybe I didn't do very well in this test. Maybe I'm not, paying attention as much as I need to in class. Maybe, all this kind of stuff. But I know where I need to go. And I know I was there. And I know there's a positive trajectory to get there, right? And I know this might be super biased. And like, I don't know how to put it. What I'm saying might be very biased and it might actually be so high level that it's not even useful for you in particular, but it's quite hard to be like very specific when you say, oh, I just went back to school for CS. Like what specifically about CS are you interested in? Are you interested in, I don't know. Are you interested in AI? Are you interested in, SQL stuff? I don't know. Like what do you want? What particularly is interesting? And one way that I find helps me get very motivated and interested is to talk to the professors about the research that they do. What are they doing to help push the boundary of human knowledge? What is interesting about that? And as you start learning about what they find interesting and areas that they find cool, eventually that enthusiasm will rub off on you, right? For example, I did research in plasma physics when I was an undergraduate. I also did astrophysics. Do I necessarily care about plasma physics? Not really. Do I necessarily care about astrophysics? Again, not really. But I found that because these people were very interested in these areas, that enthusiasm rubbed off on me, and I was able to study things that I wouldn't have otherwise studied using tools that I learned on the job, right? And so I could learn about molecular dynamics because I wanted to learn about, plasma physics. And to do that, I had to learn molecular dynamics. I learned about all the computational things I need because I knew I wanted to do computation specifically to solve these problems. where I had a group of people who were all motivated to tackle it together, Let's keep going. A silent tree, and they cannot repeatedly measure it because that would change its state. Well, if you repeatedly measure a quantum state after it's already been up or down, then, yeah, actually, let me just bring this picture back up. So you measure, let's say we measure A over here, right? Well, now we know B is going to be down, right? So if they measure B, they're also going to get down state, right? Because we already know that information, right? But repeated measurements after the initial measurement does not give you any more information. No. So it could be that they do independent measurements, that A does a measurement and B does a measurement. But what you were hoping to do is to give B the information that this is going to be a down state without them necessarily doing that measurement, right? And that would be something really influential and would be quite helpful for the rest of the quantum algorithm or the quantum circuit or whatever that they're working with, right? But that's the information that's hard to come by. Like, even though we can do a measurement and we automatically know that, what the other qubit is going to measure to be, it's difficult to, actually use that information in any useful way, right? That's what I was trying to get at. So much algebra in AI classes, it's disgusting. I actually don't know what's useful for AI. I mean, I know it's just a bunch of matrix multiplication, so you do need to know a lot of basic linear algebra. But beyond that, I don't really know how much math you need, Thank you for your advice. I would love to tell you I'm interested in X or Y, but I'm still exploring. However, what I can tell you is I like low-level programming. If you like low-level programming, that's already a really good start. Like, there's so many different areas you can do low-level programming. That was also something I really enjoy with, like, the physics research I was doing. I loved coding in, like, C or Julia or Fortran, these languages that you really interact with, like, the lower-level representation. LLVM, any type of GPU programming, all this kind of stuff was really enjoyable to me because I like programming at that level, right? And it's quite different than people who were doing like web stuff, vaguely. You know what I mean? And so with all that said, I feel like if you like low-level programming, just kind of hammer into that. Just say, yo, I enjoy this, so let me do more of that. And as you start doing more of what you like, you'll eventually figure out like what it is that you like the most. And also, don't pigeonhole yourself, right? Like, just because you like low-level programming or GPUs or something like this, that doesn't mean your whole career is going to be on GPUs. That doesn't mean your whole career is going to be on C or Rust or anything like that. Do what you like when you like it. Follow forward. Keep going with that momentum. And then eventually, as you start to feel your momentum change and you feel your desires change as either a researcher or as a computer programmer or as anything, follow that momentum. You do what you can not to feel like you're stuck in a particular area. I think people forget that a good CS degree aims to give you the foundation to learn anything in the field yourself once you've graduated. So math, algebra, set theory, etc. is necessary. Right. That is my opinion too. Like, the point of an undergraduate education is to set you up so that if you have to read any papers in the field, you can read them and understand them. If you have to, learn something on the job, you can. Like, that's the whole point, right? CS is not much about programming. I like low-level programming as well, and thus work as a firmware developer. Yeah, see, that's really cool, right? It is also something, I would argue, you don't necessarily get in a CS degree, just like, 10x Programmer is saying here, I do too. I write emulators for fun. In CS, you should get into field before graduating. Otherwise, you're wasting your time. There's some truth to this as well, right? You could argue that the CS degree in particular is very theory-focused, whereas people really prefer more applications, I guess you could say, and the CS degree doesn't necessarily set you up for that. But a lot of people who are making that argument already have a CS degree, So it's kind of, I don't know, it's kind of like they're retroactively looking back at their education and they're saying, oh, actually, it wasn't great for these reasons. And there are a lot of people who can do programming without a CS degree, right? Like, it just depends. Like, my degree is not in CS. I took CS classes, but my degree is in physics and my PhD is in, computational science. As much as I do a lot of programming and I use it as an effective tool in my job, and I've read CS papers and I enjoy reading CS papers, I don't think you could classically consider me to be a CS guy, right? I could be computational science, but not computer science. I prefer high-level languages. Hey, look, I mean, to be honest, there's a reason why I work so closely with Julia. Even if sometimes I feel like Julia is not the right tool for the job, I do agree that having a high-level language to do lower-level stuff is a good way forward. I mean, that is how a lot of programming happens. Python, in many ways, is just a front end to C for a lot of applications. Okay, let's finish up our discussion about quantum computation. Okay, so This is all stuff that we know. So we know there's, universal quantum computers don't really exist in the wild. We have all these quantum effects that we can take into account. We have Shor's algorithms, Grover's algorithm, QFTs, variational QFTs are quantum Fourier transforms. VQE are variational quantum. Oh gosh, 10x programmer Frank, come on, man. What you gave it to me. Variational quantum is the eigensolver, and then we also have the quantum approximation optimization algorithm. So this one I want to learn more about. So I'm actually going to type that one out because this is something I want to learn about. So let me just do a tab here: quantum approximation and optimization. This is one I really want to learn about. I actually did not know much about, or I hadn't really even heard of that before this stream. So that's really good to know. Let's pop down here. My PhD is in programming languages theory, but I've never really coded. I only know Haskell syntax. To be fair, Haskell is a pretty good language to know. It's pretty fun. My degree it's not in CS. I never had CS classes. I still ended up giving programming lectures that I designed myself. Man, I was in the same boat. Like, I've taught so many programming courses for OIST, for MIT. I mean, it's just, I don't know. I don't know how else to put it. Like, I learned how to do this, and I do it. Hey, Cobalt, what's up? Okay, so now let's start talking about the vibe part. This is all stuff that we know. Now let's start talking about the vibes. The vibes are very similar to that of machine learning for me. It's in this weird bubble that I'm afraid is going to pop at any given point in time, and I don't even really fully understand. Sometimes you're reading a paper and you notice buzzwords, and these buzzwords lead you to believe that the paper should not be trusted, even if the results feel like they're good results. Because of the way it was written, you feel like there's a little bit too much salesmanship here, as opposed to actual, like, useful quantum stuff. You know what I mean? Like, that's the thing I'm afraid about with quantum computing. There's just so much hype around it. It's hard to get to the actual picture. And that's why I always talk about it with respect to machine learning, because I feel like they're similar in a way. They're different. Obviously, they're different, but they're similar in how people treat them, in that there's a huge, like, just, again, so much hype, it's hard to break through, right? Although I'd like doing low-level stuff, Haskell is still my favorite programming language. QAOA looks interesting. It is for combinatorial problems. Maybe it can solve NP problems in P time. Oh, could be. But I don't know details of it either. Luckily, quantum computing is prohibitively expensive, so you cannot attach it to literally anything like you can with ML and AI. Yeah, especially right now. Like, maybe in the future, there are... This is the other thing about quantum computing. I don't yet understand. There are so many people who say that when quantum computing comes online, it's going to flat out replace classical computers. And I have not yet seen evidence to support that claim, but I'm happy to be proven wrong, right? There could be, in the future, like, just a way to create a general purpose computing device that is purely quantum, that is actually useful beyond for specific niche cases, right? That could happen. I just don't yet see how that could happen yet. Again, I'm happy to be proven wrong. Phase estimation is an algorithm that is important as QFT, in my opinion. Yeah, this is good. I should mention that up here as well. I think IBM provides a free service to run quantum computing programs, and there are simulators. That's true, yeah. Quantum computer always has to be measured with a classical one, after all. Right, this is the other issue, right? This is what I meant earlier, or what I was saying earlier with the whole, like, measurement device, and how, like, there's always going to be, like, in principle, there are some cool things happening, but because you always have to relate this back to a measurement or some sort of, like, classical channel, it's difficult to see how it's going to be useful in the long term for some applications. Are you sorting topics? How about silicon photonics? I think it would be brilliant for making future FPGAs or ASICs for data centers. But as far as I understand, it might be practical for the quantum computers too. I'm going to just copy that and put it into the paper pile on Discord. So for those of you guys who don't know, I'm actually collecting topics over here on the paper pile on Discord. And I think I can just do this, upload file, grab, that was for a thumbnail. Yeah, now I don't know where that screenshot went. Probably all the way down here, right? This one? There we go. Anyway, so I've been collecting all of these different topics on the paper pile on Discord. So if you have topics that you want me to talk about, just throw them on the paper pile on Discord, and I'll take a look at that. Well, you still want deterministic logic for most computing operations. From what I understand, it makes not a lot of sense for quantum computers to replace general computers to make dumb stuff. What I mean by dumb stuff is just regular things we do on computers. Yeah. This is also what I think is true as well. I think there are certain niche applications where quantum computing will flat out replace classical computers, maybe in the next 10, 20 years. but it's difficult for me to see it used generally because of exactly what you're saying. Like, there's just stuff like internet browsing on a quantum computer sounds like, why though? You know, like, this is the thing. It's like, why would you do that, you know? And now let's talk about one more elephant in the room. Yeah, if you could just go ahead and throw that in the channel. I'll look at that. But I also already just put that in there. So I think it's the same thing. Digital computing with silicon photonics, but also analog computing with silicon photonics. Yeah, just throw that in there, and I'll again, that's just where I'm collecting all the ideas. Faster than light internet. I think anyone who is proposing any faster than light thing at this point is maybe not understanding the physics of what it means to be faster than light. In principle, yes, it is possible to do something faster than light. I think there's something Hall problem. No, what was it? Oh my gosh. There's an experiment in my mind where we showed Alan Espay, I think, is the person who did the experiment. Oh gosh, I don't remember all the details here. I don't even remember the name of the theory that he was experimenting on. But effectively, what I'm trying to remember, the experiment I'm trying to remember, is one where we did the measurement of two different qubits, and we showed that in principle it is faster than light. It's instantaneous. But again, that information is moot when the only way to talk about that information is through a channel that is at the speed of light. So anyone talking about faster than light stuff is still purely, in my mind, in the realm of science fiction. Not pseudoscience, but science fiction. I think those two are different. Sending bits into the past. This is, I feel like I've heard this before, but I don't remember what the context is. It's dumb marketing probably. What about MLIR-based languages expanding the scope of traditional programmers' skill set at virtually no overhead cost in training? Languages like Mojo would be a killer application for AI programming, turning all these quite crappy programmers in academic offices everywhere into modern standards, really decent one. That's exactly what Julia does. I mean, I don't know if I am a Julia shill. I work in the Julia lab for MIT. It is always weird to me, like, when people talk about, like, oh, isn't Mojo like a great, like, step forward? It's like, but this is literally what Julia does. It takes a higher level programming language, drops it down to LLVM. There's a middle layer representation, MLIR, exactly like Mojo, that allows you to get the exact speed that you want out of C and C++, just in Julia this time. I think the reason Mojo is taking off and Julia isn't is because Mojo is, like, basically just Python, whereas Julia is itself its own programming language. We don't discuss crackpot physics. I have some intention, though, of looking into crackpot theories. I think they're so interesting. There's one in particular that I do kind of want to talk about, which is the oh gosh, what is it called? It's the spindles of consciousness. It's something of consciousness. Microtubules of consciousness, I think, is what I'm talking about. Let me go here. Microtubules of consciousness, I think, is what I'm talking about. Oh, I don't know. It's like quantum brain science. The reason I want to talk about this is because it is purely pseudoscience right now. Like, it's more than purely pseudoscience, but myself, as someone who's very interested in neuroscience and quantum, was looking for any correlation between quantum and neuroscience as an undergraduate, and I got sucked into these stupid microtubules of consciousness, like, rabbit hole, and I genuinely thought it was real for a long time until, I don't know, I eventually woke up and got out of it, you know? Anyway, my point is that it's something I wanted to talk about, but also I'm afraid to talk about because I'm afraid to platform these ideas. You know what I mean? Like, flat Earth is one thing, right? Like, no one's going to believe flat Earth, no matter what I say, you know? Even if I give them a compelling argument for it, they're also not going to believe it, right? But these things that are more like somewhere in the realm, like there's enough information to believe the basic fundamentals of the theory, they lead you to down rabbit holes where you accidentally learn or you accidentally feel like they could be real. And especially as an undergraduate who knows enough about different research areas, you can easily fall into these traps, right? And so this is one of those things that I kind of want to talk about. Let me go ahead and catch up here. Speaking Speaking as a math student with 5 years in software engineering, this is the most promising text that is still within reach, miles further ahead of photonic computing, quantum computing. Yeah, I think you were also the one that made the comment up here. Yes, 100%. I think actually talking about MLAR and what it means and how it works and talking about LLVM, this is all really good stuff to talk about. I also want to talk about SPIR-V, which is kind of the GPU LLVM. Especially it's interesting because Microsoft with its DirectX library has recently mentioned that the latest DirectX is going to transition to SPIR-V, which is the same thing they use with Vulkan. And so there's actually a lot of really interesting questions as to how useful SPIR-V can be as a, like, beyond just GPU compute language, because SPIR-V was originally just for OpenCL. It was extended to Vulkan, and then kind of, it's got a really interesting history, and I want to talk about it. But the other question would be, hey, if we do have these physical devices like quantum computing, how hard would it be to talk about these devices at something like a SPIR-V level? What is the mid-level IR for quantum computing? Is this standardized, right? That's a question that would be a really interesting computational science question, right? That could lead to an interesting paper as well. It's possible large-scale quantum computers aren't possible physically. Proposed experiments of Bose and Marletto-Vedral that test generation of entanglement between separate quantum systems in superposition could show that gravity causes decoherence. That is super interesting. Could you post the link? We allow links in the chat. Do you know algebraic, Julia? I do not. Another interesting thing to talk about. Mojo is also closed source, probably to do with all the AI hype. As far as popularity is concerned. So this is the thing I don't understand about Mojo. Let me just go back really quick. Nope, don't want that. What? I'm losing. Oh, it's 1 second. I got to do something really quick. So I had up Kilimanjaro. That's what I had up. Here we are. I just want to make sure I have these tabs open for our eventual discussion when we do talk about this, but I want to talk about Mojo a bit. I don't understand it. Maybe that's me. I just don't understand what... I get Julia. I get Python. I get maybe why Mojo exists, because I think it's just Julia is just Python. You know what I mean? Like, it allows for you to get the speed that you want out of Python, I guess. But I don't understand it beyond that, and I don't understand how it's tied to machine learning, for example. Penrose theory, society became a crackpot. Right, yeah, exactly that. And that was why it was also quite sad on my end. I love Julia for its purpose. I used it for integer programming before, but as you say, the syntax seems quite daunting, and the ecosystem almost non-existent compared to Python, whereas Mojo promises full backward compatibility once they reach spec parity with Python. Yeah, so the thing is with Julia, though, is you can call Python and C and Fortran without any loss in performance. So if you want to write Julia as if it's Python, you can actually just write Python code in Julia. Like, there's python.jl that allows you to do this. I personally find the syntax of Julia to be easier to understand and to read than Python. However, I do understand that most programmers know Python already. Like, they just already use it. So there isn't really a reason for you to change languages. I would make the argument that there is no other GPU language that actually does as good of a job at making GPUs accessible as Julia. But that's kind of a separate argument to have. To be fair, you can load pretty much any Python. Oh, you just said that. These things are like physics fan fiction. Yeah. I like models as models, probably not reality though. It depends on the model, right? Like for me, like certain things, you need theory behind most experiment. Otherwise, it's difficult to understand the goal, right? Like there's a reason why physicists and theorists have been like kind of, punching at each other for, hundreds of years, I guess. It's because on the one hand, doing experiments without like a clear theory or a clear goal as to what you're trying to do, I mean, these do have some benefits in like very specific cases, but for the most part, like when you're doing experiments, you're trying to validate a theory, right? It is much easier to move much faster with pen and paper or even a computational model than it is to do in practice. And so some models are quite useful, but sometimes you just kind of go too far. Like string theory is, for me, maybe I just don't understand it, but it feels to me like clearly in science fiction, right? Like it's one of these things that until someone can prove to me or even propose a way to experimentally test string theory, I kind of feel like I don't believe it exists. And I know I shouldn't say that because I know there's a whole bunch of really good mathematical models out there that, exist. It's just what I mean is these models don't relate to reality unless you can experimentally prove that they can relate to reality, is what I'm trying to say. Speaking of flat earther, they have arguments for every single theory you might have. I stopped bothering about them. Yeah, but it is super interesting to look at the theories that they have and explain why they might think that. Mind if I ask, what is sickle used for in computing? Let me just write sickle down, and we'll talk about that in a second, because I have to catch up on chat. So Soga Bows, yes, let me just go ahead and... Gravitational, this guy. Let's take a look at that guy. That's actually, let me pull it up. There we go. I'll find that paper in just a second. We might actually even look at that today. Kind of like Python. Yeah, Python was always an interesting case to me. I was wondering why people didn't use it. Mojo is made by a really good programmer, marketed speed and simplicity, and also talked a lot about AI. It's just assumptions from me about why it's hyped a little. Yeah, I just didn't know its correlation or its relation to AI and why you would... Like, what about Mojo makes it good for AI? Mojo looks cool, designed by the same developer who created Swift, which I currently use for mobile development, but haven't tried it yet. I think coming around to this Julia thing you guys are all on about, I didn't know it had implemented module compatibility from Python. I'll also have to see it for myself before it turns out like a DOM? With WASM, WASM type situation, but barring that, I will surely have to spend more time getting comfortable with it. To be honest, you will see Julia on this stream. You will. I do so much Julia programming that like you will see it. I might be doing like C for some applications, but just stick around. You know, you'll see in the stream title when I start doing Julia stuff. If you want to learn more, just ask. I'm a member of the Julia Lab and in principle a core developer of the Julia GPU ecosystem. And so in principle, if you have questions, like, there is almost no better person than to ask, you know? And I also give, in my opinion, somewhat objective views as to what Julia is and is not good at. So even though I know I'm a Julia shield, I try to be like comfortable with saying things that Julia is not necessarily good at and things that we need improvement on. Let's see. In my opinion, Mojo is popular because of VC backing. Also, they note that Mojo currently defers backers to Python for pure Python code. Yeah, so let me just see, like what I'm just gonna open up on Wikipedia. Maybe this could just be me not understanding, like, but this isn't Python. fn main, function add, def sub, add Python. I mean, this is quite different, isn't it? Yeah, it's quite different. Like this is, because this is Rustation. I see. So it allows you to do either Pythonic or Rustation. I gotcha. That's me being stupid. I'm sorry. All right, let me talk about Sickle then, because this is something I do know about. So when it comes to GPGPU programming languages, there's a couple, right? And let's just go ahead and write them down here. So GPGPU. So one and most popular one is CUDA, but you also have like OpenCL, and then you got the Julia GPU, and then we have other languages like Sickle. I gotta move this guy real quick. Okay. So let's talk about these guys. There's obviously a whole bunch of different languages out there that I have not put on this list. I'm just going to do this as a quick kind of, let's talk about it. So CUDA. CUDA is in some ways like the king of GPU computing, and it has been the king for a very long time. The problem with CUDA is that it only works on NVIDIA GPUs. The advantage is that it has so much documentation and so many people use CUDA as a programming language for GPUs that, to be honest, if you are starting to do GPUs in 2024, though I do not necessarily recommend you use CUDA, I do recommend you go through the CUDA programming guide, because it teaches you basically everything you need to know in like a couple pages to understand why and how you program GPUs, even if you're using a different model, right? Now, if you're not using NVIDIA GPUs, you might say, oh, but how do I code on, I don't know, parallel CPU? How do I code on Intel? How do I code on AMD? How do I code on Metal? If you want like something that works on any architecture, then you shift over to OpenCL. Actually, this is a good thing to talk about. Yeah, the directly run on CUDA thing. Yeah, let's talk about that too. That's actually like a really copy link, because I think there's some controversy here, and I'll talk about what I think the controversy is. So if you want something to work on any architecture, then you switch to OpenCL. OpenCL is the same programming model as CUDA, but that programming model can now work anywhere. One core difference between OpenCL and CUDA is that for OpenCL, the kernels that you're writing, the functions for your GPU code, are compiled at runtime as opposed to compile time. What this means is you're actually able to write more flexible kernels because you can metaprogram them as if they're just strings. Disadvantage is that they're compiled at runtime. So if you have a bug in a kernel, you don't see that until you're actually running the code, which has a major disadvantage for a lot of different reasons. Okay. Keep in mind that for both CUDA and OpenCL, you're fundamentally writing different code than what you would expect for the CPU. In both of these cases, what you're doing is you are writing a function that executes purposely in parallel, right? So you're not writing a for loop and then adding like an at parallel in front of it or anything like that. You're literally writing it for a very specific purpose and for very specific hardware, right? And writing kernels, GPU kernels, is significantly more challenging than writing code that you're used to writing for the CPU, right? You have to think about memory management. You have to think about shared memory tiles within specific threads, thread blocks and stuff like this. There's so many things you have to think about that you don't have to think about for the CPU, because there's just more things that you can do with a GPU and more ways to like deal with the hardware like at a lower level, right? So then comes Julia GPU, which is the one that I recommend people at least try to learn. This one allows you to write very simple code that works at the array level. So if you have like if you have a piece of code, like let's say a sort or a sum, and you have an array that exists on the GPU, like either a Q array for CUDA or a ROC array for AMD, and you run sum or sort or something like this, you can just run it on the array level and you don't have to think about that, right? You can do like a vector add, and for Julia GPU, it's just a like dot plus B, and assuming that A and B are both arrays that are on the GPU and they exist in the same location in memory, you just add them together and you don't have to think about it, right? And so there's a lot of really good advantages that you can use Julia for. Basically, the entire Julia suite, like all the flexibility and composability that you get from Julia, can also extend out to the GPU ecosystem, which is something no other language provides, right? It is just easier to use a GPU in Julia than it is anywhere else, right? But then if you do want to dip into the lower level kernels, Julia provides that with kernel abstraction. So if you want to get that speed and performance, which you also get here, you get that same performance, which is a dot plus b. But if you want to write that out manually, you can, and you get that same performance you expect. And then if you don't want to do any of that, and you say, look, I've got this CPU code, and I want just to run this CPU code as if it were on the GPU, you can also just basically do something called an at floop in front of that CPU code, and it will probably work on the GPU. And so you have like 100 different ways in which you can use the GPU effectively in Julia, which you don't get in other languages. So now let's talk about SYCL. SYCL and a lot of these other languages like Cocos, APIs, I guess I should call them, exist as ways to take like basically existing languages and to allow users to write CPU code and flexibly transform those into GPU code. Now, what this means is if you have a for loop, you can just kind of throw that for loop onto the GPU by adding essentially an at parallel macro on top of it. And this is what SYCL does, as well as Cocos and these other languages. Now, SYCL is based off of OpenCL. And so basically you could write a kernel in OpenCL, or you could write your typical CPU code and then extend that to work in parallel with SYCL. For me in particular, I don't find SYCL code to be particularly easy to understand. In fact, I kind of find SYCL code to be much harder to understand than CUDA or OpenCL, because you have to do additional things on top of just write your kernel and just write the for loop. Like, the promise is that you can write a for loop and then just throw that onto the GPU and have that work in parallel. In practice, that's not how it looks, and it's actually much more difficult to understand what's happening under the hood, because people who are writing SYCL code are basically stuck into the CPU programming model. But once you start expanding and you start thinking about what the code could look like on the GPU, well, now you can start writing code that is in a sense more flexible or works better with the hardware, right? So what SYCL is a way to basically takes, research scientists, research software engineers, people who don't necessarily want to go through all of the learning process of learning how to write code in CUDA, OpenCL, or anything like this. It allows them to, with minimal changes, write the same code that they were going to write before, and then just run that on the GPU without much thought, right? There's still some thought, but certainly you don't have to learn a whole new programming model, right? So that to me is where SYCL exists. For me in particular, because I know GPU programming and I've been doing this for years, I find it more complicated. But for people who are not in the same boat and they don't know GPU programming, it's actually probably a lot easier, right? And so that's where it exists. Where does Julia stand with TPU and NPU integration? It works out of the box right now. I really love portability with my MacBook, and just being able to PyTorch using NPS is fantastic. Julia is way ahead. Like, in terms of just like any type of Metal support, we have direct support with metal.jl. You could write GPU kernels in Metal, but also this right here, if you just write these as Metal arrays, as in arrays that are going to be using the GPU on your Metal device, it works out of the box. We're way ahead when it comes to metal integration and Mac integration, and also NPUs. Just they work. Like there's no question they work. Because Julia focuses so much on composability, we have spent a significant, like a huge amount of time building up the infrastructure, so that as new hardware comes online, we can just add that new hardware very, very quick. It actually took. Like it took us like 5 years to go from to add AMD support, and it took like 2 years to add metal support, and then it took like a few months to add any like general purpose NPU support. Like it's insane. This is why I recommend it, because it's really, really good at specific hardware. That's what's really good about Julia. I heard about NVIDIA wanting to do GPU CPU combined. How much do you think this will affect GPU sphere and the programming spheres for this? That's a very good question, and this comes back to a discussion I had before. So I said shared memory. Also 10x programmer, we'll talk about the CUDA and AMD. That's something I want to talk about, but we haven't gotten there yet. So let's talk about NVIDIA and GPU CPU stuff. So I think anybody who does GPU programming understands where this is coming from and the desire to do what they want to do. But I think anyone who does GPU programming also understands that these unified memory approaches come with inherent drawbacks, right? So up until now, this thing, I think what you're talking about is unified memory. So let's just put it down here, unified memory. That is the ability to write a code that executes on CPU memory and run that, basically flawlessly run code, CPU code on GPU memory, or run GPU code on CPU memory. That's kind of what we're talking about here. And like I said before, writing code for the GPU is significantly different than writing code for the CPU. And so writing code in a unified memory approach would allow you, assuming that the memory is actually like a hardware device, like that exists between the CPU and GPU, writing these unified memory approaches would allow you to write GPU kernels, which work very, very well for massively parallel applications, and also CPU kernels that work very, very well for serial applications. And because you can use your CPU cores or your GPU cores, you get the benefit of some things that GPUs are bad at and some things that CPUs are bad at, right? So like, you know, any type of iteration, for example, like step-by-step operations where you have to do like step 1, step 2, step 3, step 4. This is stuff that GPUs are naturally bad at. But anytime you have to do things like in parallel, like, oh, I don't know, like you have to solve, like you have to find like, do like a ray tracing simulation of every pixel on screen. This is where GPUs are quite good. So like there are advantages and disadvantages. So if you had a unified memory approach where you had a bit of memory shared between CPU and GPU, then in principle, you get the best of both worlds, right? And so this is very advantageous. Now, the problem is that as it stands right now, there aren't too many hardware devices that can do this. There's one on the AMD side that can do it. And in principle, Macs can do it, but it's not quite there yet. But the way it works right now is for most of these CPU, GPU things, you can write it as if it were unified memory, if you do the unified memory approach. But actually what's happening under the hood is an on-the-fly transfer between the CPU and GPU. And if you're doing an on-the-fly transfer between the CPU and GPU, this means that you're getting a huge performance delay, because when it comes to writing code for the GPU, the slowest part of that code is the startup and the ending phase, when you're basically getting that data back and forth from the CPU and GPU. So you want to avoid that as much as possible. But assuming there is a hardware device that allows you to do this, then in principle it's quite good. I saw this, but I don't understand much of it. Yeah, let me go ahead and take a look. Copy link, paste over here. Okay, so let's start, actually, since we're over here, let's go to the NVIDIA CUDA can now run directly on AMD. So my understanding is, I didn't know about the scale toolbox. This is actually quite interesting. So AMD is in a, what is HVM? I'm sorry, I might not even know, so I don't even have an opinion. So here's the problem with AMD. AMD has equivalent hardware to CUDA in principle. And in fact, it's actually faster than CUDA for some situations. Most supercomputers, like the biggest supercomputers in the world, they don't run NVIDIA anymore. They run AMD because AMD has the exact same performance for less cost, right? The problem is the toolkit, right? And this is where AMD always fails. Its software toolkit is always just behind what is available for other competitors, right? This is why AMD took a very long time to catch up to Intel for like the CPU space. And it's why AMD is having such a hard time catching up with NVIDIA, because when it comes to computation, almost every single person in the GPU space knows CUDA and learned CUDA 10 years ago, right? And so as you start using GPUs, you're almost always going to start with CUDA, right? And so what you want is the ability to run CUDA on basically any hardware, right? And so to fix this, AMD, there's a whole bunch of people who have like these fan projects like Zluda, which is mentioned here, which basically allows you to take CUDA code, directly run it on AMD. People have been trying to do this for a long time. But it's not usually quite there. So it's quite interesting. If this allows for people to run the CUDA code natively, then yeah, this is a great tool for people to have. Zula promises, but AMD killed it. Yeah, there's a whole bunch of reasons why they killed it. I don't know if we necessarily want to get there. Problem with unified memory is high bandwidth requirement, making memory expensive. Yeah, exactly. This is, I think, what I was trying to describe before, but I didn't do a good job of it. So let's see what they have here. Scale has been in development for 7 years, according to Spectral Compute, and it doesn't rely on NVIDIA's code, but builds its CUDA-compatible toolchain, which makes Scale highly adaptable among multiple platforms, such as AMD's RDNA. Hey, actually, this sounds great. I mean, this honestly sounds great. CUDA is a really great product that a lot of people use and a lot of people appreciate. If you can just directly use CUDA on another device, go for it. You know, that sounds great. Allowing more people to use a GPU cannot be bad. And in my opinion, maybe I'm a bit biased here, I feel like pretty much everyone in their programming classes in college should learn how to write code for the GPU. Because, I mean, if you're going to do machine learning models, at the end of the day, at least right now, they're probably running on GPU or a GPU adjacent device, something like a GPU. And so it's really important to allow users to write code and to learn CUDA from an undergraduate level. I think this is something that we should be teaching. In fact, in some ways, it's even more important to learn something like CUDA than it is to learn like a parallel CPU or distributed CPU like situations, right? Because more people will probably interact with a GPU than they're going to interact with a cluster, I would say. I don't know, maybe I'm biased there. But yeah, this is great. This sounds like it's a good project. I'm interested to see where it goes. Okay, let's go over here. We have, oh, did I delete the wrong thing? I think I did. AMD announces, oh, the UDNA. Yeah, that's what I want. Okay, and then we have this guy. Let's go ahead and copy link and open it up over here. Okay, so I think this is talking about the unified memory thing. So right now, this is what I was talking about earlier. When we talk about unified memory, like it's like really good in principle, right? It's really good in practice, right? If we are able to have a single piece of hardware that can access both the CPU and GPU, rather, we have a single piece of memory that can be accessed by the CPU or GPU, then you get the advantage of the big beefy CPU cores, and you get the advantage of the massively parallel GPU cores. And so there's obviously, this is like the holy grail. Maybe not the holy grail, but this is something that people are really, really looking forward to in the GPU space, right? And so I think this is the hardware that just allows for that to happen. And yeah, AMD has been, I think, leading the way here. At least the only devices that I know that are physically capable of doing the unified memory approaches, from what I've seen, are AMD, right? And that's great. A lot of people are really looking forward to this and seeing where it goes. Right now, it's a little bit behind, I think, what it can do technically, but in the next 10 years, I think this will be what people can do. It's crazy to me, and as always, AMD has always had this drawback at every level of their offerings: driver issues with their consumer GPUs and compatibility issues with their commercial systems. Right? It's literally like it's literally the biggest like thorn in AMD's side. They're always so good with hardware, and yet they just fail. They fail at software every way. Can you do quantum computing with GPUs? Yes, you can. In principle, you can use GPUs to simulate quantum computers. I don't know how far this has gone, but I know a lot of people are doing it because we don't have like full universal quantum computers. And so as we're starting to figure out what it means to have a quantum computer, people are doing classical simulations of quantum computation. This is very useful. It has a very clear purpose in the academic literature right now. And it's quite interesting because there are so many toolkits to do it. The other reason it's interesting is because there are a lot of people who are trying to figure out, and again, maybe I'm very biased here, they're trying to figure out if it's even energy efficient to use quantum computing for a lot of tasks. And so we've seen in a lot of cases that people have found that even theoretically, quantum computers are just going to be more intensive in terms of like energy per unit of computation, like watt or whatever per unit of computation. I don't really know how to measure it, but they found that it's actually maybe not necessarily going to be as efficient as people had hoped. So when you see machine learning, a bit sketchy. When you see quantum, maybe a bit sketchy. Quantum information, maybe a bit sketchy because there's a lot of hype around it. And if you see anything like quantum machine learning and talking about GPUs and stuff, you might want to, might be super sketchy. And if you see environmentally friendly, how do I say? like environmentally friendly quantum machine learning, at that point, it's probably a scam. Like there's a possibility that quantum machine learning is not a scam, but in like if it says like sustainable quantum machine learning, yeah, that's when it's a bit of a scam. Where's my ad blocker? I just don't have an ad blocker. I don't know. Maybe I should. Yeah, I know I probably should. So you've been studying quantum systems. Is that like sensors in contrast to computation? So quantum system simulation is basically the simulation of quantum systems via classical computers. So it could be anything, right? It could be sensors or something like this. In my case, I was doing superfluid simulation. So this would be a simulation of a Bose-Einstein condensate. And I was doing like figuring out how the vortices reconnected and all of this. It's a niche application, but it was nice for the time. Like the way I see the PhD is that the PhD is not intended to be like the biggest and greatest thing you're ever going to do in your life. It's meant to be a way to get your foot in the door and to teach you how to do research. And in that way, my PhD was perfect. I was able to get my foot in the door, learn as much as I could, and that was nice. Episode 2 of Hello People, welcome, another Leos Labs of Internet, the wonderful back. Hey, what's up? Will you do quantum computing with GPUs now? We've been rambling, but I think it's okay to ramble a bit. Again, this is the first kind of stream back in a way. I don't know. I say that a lot, but this is fine. These types of conversations I think are really worth having. What I mean to say is, I feel like there aren't enough people out there who know what they're talking about, actually talking about the stuff that they know and being honest when they don't know stuff. You know what I mean? Like there's this kind of weird vibe that a lot of people have when it comes, like they feel like if you're a researcher or you're a professor or you have a PhD, like they think that you think they're better than them, right? You know what I mean? Like they think that there's an inherent arrogance to these types of people. And I feel like coming out, just being honest and talking about things is very important. So yeah, we're a little bit delayed with the discussion of analog quantum computing. I understand that. We're not going to be doing quantum computing with GPUs right now. But I think it's really good just to answer these questions, to field them, to talk about them in an open way so that people can, we can talk. I think it's very, very important to have these conversations. What do you think there would be a possibility to use microfluidics of superfluids in such a system? Like where the utility of superfluid systems come in? That's a good question, to be honest. I don't really even know what the applications are of my PhD. I kind of tried like a bunch of times to figure it out, but I just don't know. I really don't know. Superfluids are quite distinct from classical fluids. And it's very difficult to think of ways in which the simulation I was specifically doing would be useful for the broader ecosystem. Essentially, I was looking at ring bubbles, if you could imagine. But I was also using gauge field theories, and so there could be some application there. Certainly, discussions of controlled quantum turbulence could be useful. As we start thinking about like superfluid systems. Remember, this also incorporates like superfluid helium, which could be used to cool certain devices. And so maybe there's some discussion there that could be had about the interaction between these devices and like a charged electric surface, which could happen in certain like cooling scenarios. I don't know, like there are ways in which my PhD could be useful. But again, I don't necessarily see the PhD as, again, the greatest research I'm ever going to do in my life. It's more, again, getting my foot in the door, learning about the process, and publishing some papers, getting through the whole thing. Is quantum computation situation like AKS test not viable until extremely large number? I think if I'm understanding correctly, you're asking, like, at what stage is quantum computation actually useful? And to that, I don't really know. This is actually part of what I want to learn. Like, at what stage is a quantum computer viable for like everyday use, for any type of use, right? And I don't really know the answer to that. And this is part of the reason I wanted to start today's stream, and I want to talk about it, right? I think at this point, we've kind of exhausted all of the things that I know about and that I can talk about like with conviction. I think as we start moving from this point, we're going to start moving into things that I don't know about. And that's exciting in a way. It's great to learn, and I love learning. And I hope that as we start moving into these things that I don't know as much about, we all kind of enjoy that process of learning together and trying to figure things out. In particular, the reason I titled today's stream and also titled the stream on YouTube about analog quantum computation is because I don't really even know what it means to be an analog quantum computer versus a digital quantum computer. And I think people here will already know and can already tell me. But I want to explore what this means, right? I know that there are companies, like I have two up here already. One is Quera, and the other is QEra, I guess, and the other is Kilimanjaro. And these both provide what are called analog quantum computers. But I know that these work fundamentally differently than like the computers that you expect from like IBM or Google or these. And it's, I don't know, it's interesting. I don't know what this means, right? The other thing I was going to say is that when it comes to creating an actual device that you can use, like a quantum computer that can be used at scale, one thing that pretty much everybody is focusing on and trying to figure out is how to do that with error correction. I don't know if you guys know, but in classical computation, like error correction is very important, right? Because it's entirely possible that your bit just gives you the wrong value or something like that. So how do you correct that? A lot of that is through redundancy. Like on a regular old CD drive, I guess I'm aging myself here. It was something like a fifth of the CD was just redundant bits or something like this. I don't remember how much, but a large amount of that CD, maybe it was a large amount of that CD was redundancy to deal with error correction, right? And so when you start talking about error correction, you're not just talking about 1 or 2 extra bits. You're talking about a significant number of extra qubits necessary to correct the errors if something goes wrong, right? And especially because, the quantum measurement and current quantum devices have so much errors in the measurement process, this error correction is incredibly important. What I've heard is that if you're doing analog quantum computing, the errors are much more, I don't know how to put it, but much less important, and that is, I think, very important for the future of quantum computing, right? However, you need to use a fundamentally different programming model. And in using this fundamentally different programming model, is it even possible to implement something like Shor's algorithm on an analog computer? I don't know. I really don't, Imagine the analog in this case means that instead of reading bits as value, read voltage, for example. Yeah, this is what I'm thinking as well. In that, yeah, that's what I think. Now, one thing that most people probably don't know is that you can actually do a lot of computation with analog electronics. Anyone who's done a physics degree probably already knows this because I think you're required to take an analog electronics course. But like you can do like a heck of a lot of computation just with the appropriate circuit, right? And so there's nothing necessarily flawed with using an analog computer if we can, figure out how to build the circuits up from scratch. But yeah, this is where I'm at. 1,000 qubits for error correction and only 40 of them usable. I don't know. I don't know what the proportion is, but I think it's like we need like 5 times the number of bits for error correction as it is right now. But actually, that might be something we look up. Okay, but for now, I actually want to just look at these companies. I want to see what they're doing. I want to read some papers, and I want to learn, what is analog quantum computation? What does this mean? How do we use this going forward? Like all this kind of stuff. I'm quite curious about all of this, right? So I'm going to start with QEra. The reason I want to start here is because I know there's actually a link to Julia with QEra. There's also how do I put this? A Keynote speaker who did a JuliaCon talk. Actually, I'll ask you guys. Here, let's go ahead and start where we want to start. Oh, also, let me talk about Bend. Someone brought this up. I don't remember who it was. I remember who it was. But I've seen this before. Bend is supposed to be yes, so I think you brought this up before. It's supposed to be a much more effective way to do GPU programming. And I think these types of things are really useful, right? I think it's really, really useful to think of how you might structure your programming language in such a way that it takes advantage of massively parallel systems. I think that's incredibly useful. I don't know whether this one's going to catch on, right? Because we keep seeing this time and time again where people do try to dethrone CUDA, and almost every time people just go back to the CUDA programming model, right? It's in part because that's what people know, but it's also in part because it's a pretty good model for most things, So yeah, it's a question, right? Like the market for people who would be using something like Bend are probably the people who thought CUDA was too complicated. But at the end of the day, in order to get Bend to work, you might need a significant more number of caveats, of things you need to think about that you wouldn't have to think about with CUDA. And this is what I don't know, right? Because I've never actually used Bend purposely. Yeah, I don't know. A parallel language. With Bend, you can write parallel code for multi-core CPUs and GPUs without being a C and CUDA experiment. With 10 years of experience, it feels just like Python. What I will say is the following. I think a very interesting approach is actually what we're doing with Dagger in Julia. So Dagger is actually a scheduler, right? It's not necessarily a CPU, GPU. It's not necessarily a massively parallel computational toolkit, right? But what is interesting about Dagger is that it's a very simple way to do parallelism that you would not be able to do in many other languages, to be honest. I'm being a shill for Julia, I get that, but because Julia gives you such flexibility in how you want to write code to execute on any array type, if you just write code that executes on a GPU array or a CPU array or anything like this, and you have just natural functions that work for this type of programming, right? Then you can just run it in basically a Dagger block is what I'll say. And if you run it within this block, Dagger will automatically schedule things to make it so Dagger will automatically schedule things so it works on the CPU and GPU at the same time. It even has this thing that allows you, we'll see how fast it's running on the CPU and how fast it's running on the GPU. And if it's running faster on the CPU, it will prioritize GPU computation. There's just a lot of this flexibility that exists in Julia. And so a lot of times when people show me these other languages, not necessarily like Bend, but stuff like this, I find these problems have already been addressed and solved in Julia. Admittedly, Julia comes with this whole host of other issues, right? In that precompile time is often quite long and all this kind of stuff. But I feel like we've already been addressing these in Julia in a way that it has not been addressed as well in other languages. Does this mean that Julia is the next big thing in computation? No, not necessarily. But I just feel like as Julia starts to mature more, I'm hoping that people start to see its benefits and consider it as a language for most general purpose computation. There's always going to be a situation where you need Rust. There's always going to be a situation where you need C. There's always going to be a situation where you use some other language. But Julia has its uses, and I just would like people to see that. So in part, one thing that I'm quite interested in is seeing as how quantum computation is kind of sort of taking off in a way, even though I still don't fully understand everything about it. I'm curious to see what I could do as a member of the Julia Lab, how I could help maybe get some real programming languages in and start addressing some hardware issues with these quantum devices. I don't know if it's entirely possible to do with Julia because the Julia runtime is so big, you might just not be able to use it for certain applications, but maybe you can. I don't know. Hardcore Julia shill, but I'm all for it. A very informative one at that, as opposed to the usual Python Rust fanatics. I know what I know, and I know what I don't know, and I try my best not to say things that I don't have clear evidence to support. This is, it's one of those things. I once gave a lecture on Julia to a company of, someone I'm related to. I'm not going to say whether they're a friend or family member because that might be too, I don't want to dox them or anything. Anyway, it doesn't matter. I was giving a lecture for one of their companies on Julia, and I was explaining Julia. I did it through an n-body simulation, which I find is a really nice example to explain how to do parallel programming. And I talked about the advantages and disadvantages. I said, here's what Julia is good at, here's what it's bad at, here's why you might want to use it, here's what you probably can't do, but we could do in the future, all this kind of stuff, right? And that's how I always talk about it. And at the end, or in the middle of the lecture, I said, I'm a Julia shill. And then someone else said, yeah, you're a really bad Julia shill. And I didn't know how to take that. On the one hand, at the time, I said, I tried to take that positively, right? Because I was like, hey, look, I feel like I'm doing I'm doing my best to be as objective as possible about this particular topic, right? Because I don't want, the worst thing you can do is to hype up something and then to have people enter and do that thing and not feel the same hype. You know what I mean? If you hype up a video game, let's say, and people actually play the video game and they hate it, well, that's awful. But if you explain to people, hey, this game is a bit different. Here's how it's different. I quite like it, and I would like you to join me in playing it. That would be really fun. And then people join it, and they actually enjoy their time. That's a completely different vibe. They feel like they felt a gem, or they found a gem in the rough. You know what I mean? As opposed to feeling like they were sold the world and then not given that back, right? And so this is why I try to be as objective as possible when I do talk about things that I really appreciate, because not everyone is going to feel the same enthusiasm I have. But the best I can do is to give them a realistic impression, with the hope that when they join, they feel like this is exactly what they expected and even better, right? Karthik Chan, thank you so much for following. Really appreciate it. I don't have notifications up on stream, and I'm wondering if I should. Let me explain. So I used to have notifications on stream, but I took them down because on the one hand, I appreciate everyone following. I really do. I appreciate people who used to subscribe when I allowed people to subscribe. And in fact, I might turn the subscriptions back on. I've been thinking about it. I'm not entirely sure. But I have the notifications off because I like to flow a bit, and I don't like to be interrupted in that flow. And also, this is a YouTube VOD afterwards. And so I kind of don't want like people on YouTube to see like random notifications pop up. Like, we're talking about quantum computation, and then like all of a sudden, like, I like to fart 2000 has followed you. Thanks for following. It's like, it just kind of, I know no one cares, but like in my mind, it kind of like drops down the level of discussion that we're having a little bit. On the other hand, if I do allow for subscriptions again, which I could allow for, I am more than happy to have some sort of subscription or like notification for that. I'm not sure. Anyway, let me go ahead and catch up. I missed some stuff in here. I cannot bring myself to fully spell out function when writing code, and then end after each function instead of... Actually, to be honest, I agree with both these takes. I find C syntax to be actually the most elegant of the syntaxes that I know about. I really enjoy writing C code. And in part, it's because of the braces. It's because of the way functions are defined and all this kind of stuff. But on the other hand, like, it's syntax, right? And syntax is, in a sense, a very small part of the language. What matters more is the composability between functions and packages and all this kind of stuff. What matters is how the code actually flows and works together. That matters. The syntax of function and this type of stuff, it's annoying, certainly, if it doesn't like look nice. But I mean, look at Python syntax. It's hardly what I would say good syntax. It's very difficult to read a lot of times, and because of it's like harsh dependency on spacing, sometimes your coworker will use tabs and you use spaces, and then all of a sudden your Python code's all mixed up, and you got to figure out exactly why it was mixed up, and you can't quite figure it out because your IDE isn't highlighting the text appropriately or highlighting the white space appropriately. Like, it can become a mess, right? And so it's fine. Like, that's my opinion on Julia syntax. It's fine. The one-based indexing, it's fine. I don't like it. It's fine. Like, I don't have a very strong opinion on that. But the composability, I do have an opinion on. I think it's pretty good. There's an overhead to learning a language. And having a limited community of people understanding what you're doing is problematic because it cuts out the ability to collaborate. I agree with that. And I don't know what I said to bring that topic up, but I agree with that statement. Follow notifications, no point. So new switching languages is always problematic. I agree. But I got a mail notification. You did? Oh, good. I won't get to the composability if I cannot get through the syntax. I think there's a difference here between what we're talking about, though. I think what you're saying is you're saying that the syntax of Julia is so bad that you won't ever get to the composability. And what I'm saying is the syntax of Julia is good enough that it probably won't turn people off, right? Like, it's at least better than Python, right? I know it's very difficult to be better than Python. Like, it's very difficult to be like worse than Python because Python syntax is some of the worst syntax I've seen in almost any language, but like MATLAB excluded, but it's at least better than Python, right? Like, we can at least say that, right? In my book, from what I've seen. So I mean, like, Python is so bad, right, that people willingly choose to use MATLAB over Python, even though Python has the same toolkit, right? Like, in terms of scientific computation, like, you have to be really, really, really bad so that people are more willing to use MATLAB over Python, right? Let's see. As a failed computer scientist, science graduate, I can understand. That's great. That's exactly what I'm hoping for. Solution, kill a guy using tabs. Whoa. Look, I do not recommend... I don't recommend that. I do not recommend this at all. Now, should we take all the people who are using tabs and put them on an island? Who's to say? Should we provide food for those people on the island? Again, who's to say? But I certainly do not recommend any type of violence against tab users. I think that's totally fine. You know, it's like saying you're better at running than someone with no legs. Explain that. I don't actually fully understand the relation there. What I am saying is that, like, 2 spaces for the win. Okay, now we can all agree that this person needs to be banned. So let me just go ahead and get that over with. No, anyway. Python syntax versus other syntaxes. So you are saying that Python syntax is... Wait, are you saying Python syntax is good? Because you might be right. Maybe I'm incredibly biased here. No violence, but they don't deserve the fruits of our society. Yeah, maybe that's what I meant. No, for me, I find Python very difficult to understand and C to be quite easy. But this is obviously very biased because I feel like, I think everyone tries to start programming with Python and then they kind of it doesn't quite work. And then they realize, oh, actually C does work. Because C is like a lower level language, it makes more sense to my brain, which likes lower level languages, right? And so for me, Python was always just kind of like this, it always feels a little uncomfortable to use. But I do recognize maybe I was too harsh earlier, and maybe I shouldn't have said, oh, it's easy, it's so bad, If you say that you have a better syntax than Python, it's like saying that you run better with someone that has no... I see. I got it. But Python is used to develop a lot of applications. This is true, right? That's the thing, right? I also fully recognize that Python is like the front end for C for almost everybody, right? Like when you're developing C code to get people to use it, you develop a Python library for people to use that, right? It's not necessarily... I think this is my point when it comes to syntax. I personally don't like Python syntax, and I know a lot of people who don't as well, right? And a lot of people have trouble transitioning from other programming languages to Python, actually. And I'm one of those people. I find like a lot of things that Python does to be weird and not what naturally would happen in my brain. But the syntax is good enough. It's fine. It's okay. And being good enough 20 years ago was good enough to get a lot of people on board. And we get a lot of people on board. They're all developing packages for Python. All of a sudden, the reason people use Python is specifically because people use Python, right? And once you hit that critical mass, and there's so many people using the language, all of a sudden you have a whole bunch of packages, a whole bunch of libraries, everything using this language, and it's hard not to use it, right? And I feel like that's what happened with Python. I'm not keen on Python syntax myself, but as an undergraduate and the resident programmer guy, I find myself interacting with complete programming 101 noobs, and explaining Java syntax to those guys compared to Python syntax is like a night and day difference. Oh, 100%. I think Java, especially any object-oriented programming language, is dead, like, on arrival when it comes to a lot of these, like, programming 101 noobs. You know what I'm trying to say? It's one of those things where I knew someone was going to post that. I have an absolute hatred for MATLAB, and I think everyone here already knows that. Python, what is Python? Python with braces. Oh boy, Python with braces. I would almost be into this. To be honest. Might not be bad. What language do you recommend a beginner like me? It really depends on what you want to do, right? Like if you want to do some sort of ML application, machine learning, to be honest, Python, TensorFlow, PyTorch, this is the way to do it, right? I mean, there really is not other competition there. If you want to do scientific computation, I'd recommend something like Julia. If you want to do systems level engineering, Rust, maybe C, depending on how much you want to learn. If you want to do web stuff, well, there's a whole bunch of different languages for this. So what I recommend for beginners is not to, how do I put this? It's not to focus so much on the language, but to focus on what you want to do, and then to learn the syntax to do that thing, right? No, don't do x86 assembly. Do not do that. That is a bad idea. JAX is pretty up there with the researchers nowadays, and TensorFlow is suffering a slow death. That's probably fair. I have my issues with JAX as a toolkit, but I understand that I also have issues with TensorFlow and PyTorch, and so maybe I'm the biased one here. Are you a software developer? I do research software engineering. So what research software engineering is people are doing large-scale simulations. In my case, they're doing the simulation of molecules on supercomputers. And I'm the person that just kind of makes that code work to some extent, right? So I'm either writing the code to do the MD simulations, or I'm making the code they write work on different architecture that it wouldn't work on before. I'm just kind of like the glue guy who just kind of makes their code work. But I used to do a lot more... No, I mean, I do software development, right? But I don't know if I'd classify myself as a software developer, is what I'm trying to say. In practice, my title is software engineer, I guess. But again, I don't associate myself with... I associate myself more as a researcher than a software developer. All right, guys, we have been streaming for 1 hour and 48 minutes, and I've been rambling a lot, and I feel like We have done nothing with analog quantum computing. But again, like I said before, that's okay. It's totally okay to have these conversations because the point of the stream right now is not necessarily to get work done. It's to engage people at a level that we don't typically engage people, especially not on Twitch and on YouTube, and to have these conversations. And I think it's totally fine to talk about that. As long as I don't have to use overhyped tech, I'm happy. Yeah, I mean, yeah. Research software engineering is the rare type of scientific programming that actually knows how to program good software. Yeah, good, obviously being a relative term. Like, I know, like, the code I have written is like in Julia GPU, and like I am a core developer of the Julia GPU ecosystem, but also I would never say I write good code. I write code that works, that is tested and has documentation. That's about as far as I can say. What architectures are you currently working on? So I do heterogeneous code. So that means that I work on CPU, parallel CPU, and distributed CPU as well. And then I also do every GPU vendor. So that means I do NVIDIA, AMD, Intel a bit, although honestly, I don't know why okay. Intel is supported, it's fine, we do Intel. And then Metal as well. And so we just make sure that the code works on all of these different architectures. And that's what I do. So all GPUs, parallel CPU, although, again, I'm interested in quantum computation, which is why I'm doing this stream. However, guys, it is currently 3 o'clock p.m. I've been streaming for 2 hours now, and I do want to actually start talking about quantum computation. I can't believe how a few good programmers exist in research. It's astonishing how these people use computers all day and almost as a point of pride refuse to be good at it. Once you spot a good programmer who is a professor, it's like seeing a shiny Pokemon in real life or something. I actually did a video a long time ago about research software engineering and how it was a rant in a way, talking about how like the majority of science nowadays is done via software engineering, right? Software is the foundation of modern research, whether people want to admit it or not. You are pretty much always going to be used. Not always. There are still people who do straight experiments. There's still people who do straight theory, but you're probably using computation in some way, shape, or form, right? And so if you're using computation, you have to make sure the software developed for that computation is actually good. Like it follows proper software practices and stuff like that. Like you can't just hope, you know, like good software engineering is essential to good research. If you don't have that, and at the very least, you're not showing your code in your paper, I can't trust the results, right? Like I've been bit so many times by reading a paper, thinking it's interesting, thinking it does something that I've never seen before, thinking it's cool, pushing the boundary of human knowledge. And then when I actually look at the code, it's doing something completely different. And that different thing is so different, in fact, that I just can't even trust the results of the paper. Like this has happened time and time again. And it's just due to bad software engineering practices, you know, that are prevalent in research. Frozen Obscurity, hey, thanks for following. What about embedded systems? Are they used for computations? Specifically for scientific computation, no, but yeah, there's a huge community of people who do embedded systems. A lot of this is done in Rust, but there are other languages as well. It's because programming is a chore to most people, so people only learn the bare minimum they need to get the thing they want. That's true. That is completely true. It's a tool, right? And you know, who cares whether you keep your axe all shiny at the end of the day, as long as it's actually working to cut down a forest? You know what I mean? Like, it doesn't have to necessarily be you don't have to be the best at using the tool, as long as you're using it and you're getting the job done. That's fine. Good. Okay. So let's actually start talking about the analog quantum computation. Again, this is me learning with you guys. So if you guys have specific comments, questions, concerns, anything like that, let's explore it together. And let's hope for the best. So there's a couple different ways we can go about this, right? You got to clean your weapon so it doesn't jam. I feel like that is, there's truth to this. There's definitely truth to this. But I don't really know how many people would actually like, I don't know. It's hard to convince people who are not programmers that they should be using proper programming practices. Guys, I really got to blow my nose. I will be right back. I'm so sorry. I'm super snuffy. I don't know why. I'll be right back. 1 second. Okay, I'm back. If you use a hammer, sure. Is there any roadmap For learning analog computation. Analog computing is quite different, right? Like when you say analog computation, you're talking about like analog electronics. And so this would be like transistors and stuff like this. It's quite different. Wizzy Face, hey. Hello, I'm Dr. James Schloss. I got my PhD in 2019 from the Okinawa Institute of Science and Technology. And then I spent a year working for MIT doing climate science. But I wasn't very good at it, so I quit. And then I did content online with 3 Blue 1 Brown for a year. And I wasn't very good at it, so I quit. And then I am now back at MIT, but I don't feel like I'm very good at it. So I'm in the process of having a midlife crisis. Anyway, dust off the old abacus. Oh, man. I feel like I knew professors who had that. I ended up in software development because of research. I was doing non-CS masters one day, and my professor was like, "Gotta learn MATLAB," and that was the start. Oh boy. Oh boy. Oh, let's not do MATLAB rants. Let's not do MATLAB rants because otherwise we're gonna be here all day. I feel like one day we should just do a stream that is entirely how much I hate MATLAB and why I hate it so much. Like, that's it. Like, that's the whole stream. It's just a rant. We'll be here for literally 6 hours talking about how much I absolutely hate this language. But my feelings on it have waned a bit. I'm not as angry about it now that I don't see it every day. That's it. Rewrite MATLAB and Rust. No. So you have to rewrite MATLAB. Honestly, if MATLAB boiled down to LLVM, I wouldn't be so upset. To be fair, their IDE is nice. To be fair, like, most people are using MATLAB because of the plots or the IDE, or just because that's what they know. It's like, to be honest, it sucks that when people move to Julia, they actually don't like the plot. Like, they can't transition because the plots aren't good enough in Julia, right? Like, this is, like, I can't even offer them an alternative. But what they're using is just so bad. I'll definitely be entertained with MATLAB rant. Yeah, I feel like if I did a MATLAB rant episode, like, I don't think you guys understand how angry I would get. MATLAB has really good tooling for embedded systems. So, what's TODL? So I'm TODL. I guess. Okay. So guys, we've been here for 2 hours. I've been ranting the entire time. Let's actually. Or so I'm told. Clearly, that's what you meant. Okay. Let's talk about analog quantum computing. I'm actually just going to read these websites. But before doing that, I want to talk about something. So there is a Keynote Lecture 2024. Catherine? Hiat, JuliaCon. Surely this will find it, right? Why use Julia for quantum computing? Okay. We've got 2 different ways that we can go here. So when I did not contribute to QEra, no. When we're talking about using analog quantum computation, right? I am specifically interested in how we could potentially use Julia for this type of thing. And so there's 2 different ways that we can start. One, we can start by actually just watching this video. This is someone, Katie Hyatt. Actually, I don't know how to pronounce her name, but this is someone who does quantum computing in Julia. And we can just see what the current state of the art is for Julia in quantum computation. This might be a good way to start because it could be a good overview for what is currently possible with the technology we have, and then we start drilling down into analog quantum computation specifically. Or we could just start drilling down to analog quantum computation and see what's going on there. Do you guys have a preference? I am willing to do either one. I'm not a React channel, so I've never done this before, and I'm a little bit sketched out by doing React content on stream. But I think maybe it's okay because this is like very clearly educational, and I have no intention of like, I don't know, stealing the content. You know what I mean? Like I'm intending to like learn from it and go from there. Okay, I think I'm gonna watch this video. I intended to a while ago, and we can go from there. There is one thing I have to do really quick. I just got a notification on Slack, and I have to check it out. 1 second. 1 second. Sorry. It might be. Okay, good. It was not actually too important. You know, I'm still kind of technically like on call, so if someone needs something, I need to help out with that. Everyone does react in much harsher terms. You're fine. Yeah, I know I'm fine legally. It's probably okay. It's just I don't like doing React content, but on the other hand, I think maybe it's worthwhile. Again, we're learning together. I don't like learning from videos, but everyone has said that this is what you want to do. If you want to learn quantum computing in Julia, you should just watch this talk. So we'll do it. Let's just go ahead, pop in, see what we can do. All right, I'm gonna full screen this bad boy, and then we're just gonna watch it and we're gonna talk about it. Let me increase the volume a bit.
Welcome to the last but definitely not least the keynote of JuliaCon 2024.
Can you guys hear it?
Our keynote speaker is a very important member of the Julia community, program chair of JuliaCon and applied scientist at Amazon.
Oh,
So
I just
I'm
realized I
glad to
don't have
introduce
chat up.
Catherine Hyatt, who will tell us why she uses Julia for quantum computing. Please join me in welcoming the speaker.
Thanks so much, Luca. So I have to confess, while I was preparing for my talk today, I was really confused because I kept seeing on
Yeah, so they actually, the stage is outside. It's quite,
the slides.
I don't know how to put this, but it's quite weird. They have like the stage that's outside in the middle of an arena. It's like a very popular arena in the area. It was like a crazy venue that they had for JuliaCon last year.
Dr. Catherine Hyatt. And I was like, oh, I bet that person's talk's going to be really good, but I don't know who that is. Because even my own mother writes Christmas cards to me as Ms. Catherine. So I had a little bit of a struggle figuring out who exactly was giving this talk today. But hopefully I'll be able to explain to you sort of the advantages of using Julia for a lot of different tasks in quantum computing, some of the things people today are thinking about, and opportunities for people in the community to contribute. So when we
Let me go ahead and pause here. The audio is coming through. Let's see. Okay.
talk about quantum computing, we should be a little bit more specific about what exactly we mean, because there's a lot of different things going on under the umbrella of the field we call quantum computing. So we can talk about using Julia for things like designing quantum devices, simulating those devices using classical computing. And then when we've actually built the device, trying to calibrate and control it using the microelectronics we need to actually make the device do what we want. And from there, we can also discuss things like constructs and algorithms for actually programming the device at a high level in a way that's sort of more feasible for human beings to read, write, and think about. We can think about problems that are probably pretty familiar to anybody who was watching the main stage talks over the past couple days. Things like IR lowering, figuring out the types of various objects, trying to translate constructs that are more familiar to us from classical computing back to quantum computing. And then sort of algorithmic implementations of things to control and deal with errors and noise. Again, anybody who's been watching talks here on the main stage for the past 3 days can probably understand the importance of dealing with noise. So that's...
I'm going to pause it here. So there are a couple things here that I think we're kind of interested in. The one that I know Julia's already doing is classical simulation of quantum circuits. We also have implementation of error, mitigation, suppression, correction. This is very important. Like all of these are very important and stuff that we have talked about just recently. But I think the one thing that I'm quite interested in is this lowering high-level programs to IR and IR translation. So just to catch everyone up, make sure everyone's on the same page. IR is intermediate representation. So when we talked about Mojo earlier, they talk about a mid-level intermediate representation, MLIR. Julia does the same thing, where there's this mid-level intermediate representation that is, you have the Julia version and then an LLVM version, right? And so the interesting part of this talk will hopefully be, maybe, about how we can use Julia's IR on a quantum system. That would be the best I think I could hope for. But one thing I'm going to do really quick is I'm actually just going to go into downloads here. And I'm going to do YouTube. Oh, I don't have YouTube DL. Maybe I will very quickly get YouTube DL. And just download it so I can play it like off the website. I cannot. So let's go ahead and CD into builds. All right, let me just do this on the big terminal so you guys can see. Sorry, this is me. I should have prepared for this beforehand. Okay, so we're going to CD into builds, ls here, AUR fetch, YouTube DL. Sure, CD YouTube DL, ls, make package, I forgot, make package S, right? Oh gosh, someone's going to be an Arch user and they're going to be really pissed off at me doing this. More PGP signatures cannot be verified. Do I need to download the... I might not be able to do this. What OS is this? This is Arch Linux. What am I doing? This one. Reinstalling, so that's not important. Sudo pacman -syy. Try it again. And let's do this. Yes. Good. And now let's try it one more time. Make package S. Okay, look, there's a problem here. So my goal was to do YouTube DL so I could just download the YouTube video and we could watch it locally. But that's not going to be the case. So for today, we're going to have to... is the Arch Linux healing up to date? I mean, I think it is. Anyway, it's okay. I just did Pacman SYY, which just syncs all of the packages up. It should be fine. We don't have to do Pacman cache purge. It's okay. I'm using some fork of DL. Screw it. Let me just cd builds. All right, we're in build. CD backup directory. ls here. Remove -r YouTube DL. Yes. All right, perfect. YouTube DL. Let me just get this version. Screw it. I'm okay. And we'll just build it locally. I'm done. It's too much effort to worry about this. So code, grab this guy. All right, let's do git clone here. Yeah, so just for the record, the only reason I'm doing this, like the reason we're doing this sidetrack is literally just, oh, you can hot patch the make package signature thing. How do you do that? Anyway, the only reason I'm doing this is just so we don't have to watch it on the website. That's it. That's the whole reason I'm doing this. And it's a side tangent. We don't have to do this at all. But here we are. I mean, you're watching me, right? So you must be okay with me doing stupid stuff. For now, let me just go ahead and drop this back down to there, I believe. Turn the music back on. And let's keep going. So we'll get this built and downloaded, then we'll watch the video. The only reason I want to do this is I was finding it hard to figure out how to full screen the video and also watch chat. I don't know, it was hard for me. So not watching on the website is an instant win. Arch does not have YouTube DLP. Oh, maybe it does. Let me just do AUR search YouTube. Let's see, watch YouTube videos with MPV while saving the video to disk. Maybe we just do watch git. Go to package build file and look at the list of sources. The GPG signature field for the source package can be replaced with skip. Oh, but isn't that quite dangerous? Okay, teach me. I thought that was very dangerous, right? I thought that would be something that like you only do in like the worst, like if you absolutely have to. Can you just open it in MPV or VLC player? Can you? Can I just do MPV? Let me just try this. MPV with this URL. Let me see what happens. Control V. All right, let me see what happens if I just try this. If I can do this, screw it. That's what I'm gonna do. Did it work? No, it said exiting. Let me try VLC then. Did that work? Continue. No, it didn't work. If you have YouTube DLP, it should work. I don't think I have that one. I think that's the problem. That's what I have. You have at the end. Oh, I have at the end. Okay, let me try that again. Thank you. Control C. Try this again with MPV. There. Did that run? Exiting with errors. Let's try VLC again. Did that work? No, it didn't work. That is okay. We'll just get YouTube DL built and then we should be good to go. CD YouTube DL ls. Can I just do make? Setup.py. Is the mainline Arch repos in extra? Oh, I can just do, okay, let's try that. YT DLP. Yep. And then if I try this over here, should it just work? No. Make clean. Make. Oh my goodness. Command not found. Sudo pacman-s zip. For anyone wondering, yes, obviously Linux is much easier. Should work with MPV. Let's try MPV. Hello? Hello? No. You can also use normal pip. Can I? Man, you guys are all much better than me. Let's do make. Okay, ls here. YouTube DL. DL, and we're just gonna grab this guy. Oh, where is it? Here. There we go. Does it work? Unsupported URL, https youtube.com. It depends on how you on your shell. You need to quote the URL. Oh, let's try that one. please. Hello. Oh, it's working, kind of, maybe. Ho, ho, ho. Hey, guys, you are all geniuses. I don't care what your mom says. You guys are all geniuses. All right, so we're going to pop this guy up here. We're going to have it right there, and we're going to listen to it. Oh, hello there. You are taking forever, aren't you, babe? Let's just YouTube DL this bad boy. All right, so we're going to grab this. We're going to do this, and then we're going to YouTube DL here. And then I'll figure out how to do this better later. It's downloading, but it's forbidden. All right. Wait, I think you have... Wait, I think you don't have the right parentheses. Wait, parentheses. You can always use pip, infinite recursion hazard. Okay. I had it playing, but the problem was it was Python 3, YouTube DLP. I think I have YouTube DLP now downloaded because I could play it in MPV. But the problem was when I play this, I think the quality is too high and it's just taking too long to download. See, it's I'm not doing anything right now, but it's like jittering a bit. You know what I mean? So I have to kind of wait a little bit, I guess. Wasn't sure if the URL parser was getting confused. It could have been. Oh, we can do a resolution 720 URL get 720. Oh yeah, hey, you guys are great. Let's grab this bad boy. All right. Oh, I don't need the to get 720p version. So we put the URL in here. Copy link. V. There. Oh, what's the last character here? A. There. Try that. Oh, I'm an idiot, guys. See, this is a problem. You guys are watching a complete and total moron. All right, we go here. YouTube DLP this bad boy. And see what we got. Hey. There we go. We got this working. And then we'll just play it locally. I think from now on, I don't want to play anything on the YouTube website unless I can like avoid it. So I think I'm going to just try to like download things and watch it off stream. So it looks like it's working, which is great. I just have to remember to use YouTube DL from now on. I mean, we're going to have to wait like a minute before watching any videos if we do any type of React content. But I think it's generally better because it means that we don't have ads. And also like it allows me to see the chat a little bit better. There's a lot of advantages here. So I think it's totally fine. Also like, yeah, okay, maybe I'm cheating YouTube by not watching with ads, but it's okay. This is a type of knowledge that I learn and forget in a day. That's, I hope, I don't know, if we use it more, I'll remember it. Make sure to download the ads as well. Oh, that's true. Hey, what kind of ads should we download halfway through? The wrong URL? Real-time airborne magnetic navigation with magnev.jl. That is definitely not the right one, is it? Real-time airborne magnetic nav. Oh, let me see what this is. Dude, it's moral of cheat YouTube. It's moral to cheat YouTube. Wait. Let me see what we're downloading here, okay? Wait a second. Okay, wait a second. What are we downloading? Random graphs with Julia graphs. What is this? Max entropy. Is this different than before? Am I downloading everything? Like, am I downloading the entirety of JuliaCon? It downloads a playlist. I downloaded a playlist. Why do I want to download a playlist, guys? Guys. Here I was thinking you were my savior. Turns out, you just had me download an entire playlist. What am I... probably... Julia... star? No, what am I doing? Star Julia star. Maybe they are live video chapters. Can I just share this bad boy and grab this copy? You put the wrong URL. I must have, right? Okay, so here's what I'm gonna do. I'm gonna CD projects, CD videos. LS here, we're gonna do make directory stream. Oh, I already have stream. CD stream. LS. Make directory react. CD react. And now we're gonna do YouTube DLP. What was it before? Guys, I know what I'm doing. Just trust me. All right, so we're going to do 532, and I just want to make sure we have the right URL. So we're going to grab this bad boy, paste it there, and then I'm going to do this and that, except I don't need, I don't know why it does this, that, and then hopefully, if I do this, it's going to work. Give me something. Let's see, Keynote, why use Julia for quantum computing? This looks correct. Thank you. How are you, now you're asking us to do things that are impossible. Control R in shell to do a search. I know Control R, but to be honest, I prefer grep. I don't know why, I just prefer grep. But it looks like we're downloading the right video. I'm so sorry about that, guys. Welcome to Leo's Labs. Remove all the extra args except V equals. Yeah, okay. We figured it out, I think. If the URL is a playlist, it'll download all of them. We don't have the time to download a playlist, at least on stream. Yeah, I'm so sorry. It seems Julia themed. Is it trying to download a playlist? Yeah, everyone caught onto the playlist thing way before I caught on. I'm so sorry about that. Good news, you guys are much smarter than me. That's great. Another really good thing that we learned here is that Linux truly is much easier than Windows. I cannot even comprehend how we would do this in Windows. We'd have to click on something? Nah, it's hard. This is way easier. Just basically use a random like command line argument that someone posted into chat. I don't think he wants the entire playlist either. Okay, so let's do ls here. Looks like I have the MP4, so let me just do mpv. Why I use Julia, enter. There we go. 720p version is okay. Let me turn the music off, make this a little bit louder. Maybe something like that is okay.
Welcome to the last but definitely not least keynote of
How's this,
JuliaCon
everyone?
2024. Our keynote speaker is a very important member of the
big.
Julia community, program chair of JuliaCon, and
I usually use
applied
GUI front
scientist
end for
at Amazon.
UTDL. I could have
So
done that.
I'm
I
glad
probably
to
should have
introduce
done that, but
Catherine
I didn't know that
Piatta,
existed.
who will tell us why she uses Julia for quantum computing. Please join me in welcoming the speaker.
Yes, my own of a shoe.
I'm going to catch up to where we were just a second ago, which was, I think, here-ish, near the end of the slide, I think.
So what do we think of as Julia's strengths? Well,
Okay.
I think for this audience especially, this is the last keynote. I don't have to motivate this too much. We, of course, know that Julia is highly performant. It has great routines for linear algebra, numerical integration, PD solving. It's easy to compose tools from a variety of packages, which is great if you have a lot of different packages that are all working together in the same ecosystem. This means you don't have to constantly reinvent tooling necessarily. We have a strong ecosystem for...
I'm gonna pause right here, and I want to point out something that I think maybe people hadn't noticed yet. I hadn't noticed until just this moment. It's very important. This is a 55-minute video. How did I not know? 55 minutes. We're gonna spend all afternoon on this. Oh, that's okay. It's good to spend the afternoon on this. 55-minute video. Man, I'm a React streamer now. I spent all that time downloading this video, and now I'm like, but do we actually need to watch it? Could we maybe just like skip through bits of it? Okay, we should watch it. I think it's important that I at least understand. But like, it's crazy to me. It's absolutely crazy to me that people are like, hey, you know what? You need to learn this thing about Julia. Watch a keynote presentation. I'm like, sure, okay, that sounds great. I was thinking like 10, 15 minutes, not 55 minutes. You know, I guess a keynote has to be long. But we'll go through it. Let's just kind of keep watching until I feel like there isn't much more to say. Much less probability for errors. I'll go grab T. Yeah, go ahead. We could do 2x. Anyway, let's keep watching.
Probabilistic programming like Turing.jl. And what's also very important is that we have a really big community that's really happy to start working with early stage technologies where things are changing very quickly. And our community is really willing to adapt as things change over time. For example, when I started using Julia, my first Julia was like 0.4. If anybody remembers Array Apocalypse, that was a very sort of disruptive change, but it was for the better. And as Julia has evolved, we've also experienced these kind of pretty paradigmatic changes that kept the bones of the language intact, but we had to adapt to as we go. And I think this is a really big strength that we'll see called out throughout this talk that makes Julia a really great tool for this community. So 9 years ago in JuliaCon 2015 was my first talk. You can see there's a little screenshot there from
kind of fast forward
and
just a
also
little
the
bit
top
here.
picture.
Give me just a second. We're going to go past this slide. I understand she has gray hair. I get that. Okay, quick legend for this talk. So this is multiple PhD theses can have been written on this topic, opportunities for the Julia community. That's actually really good to know. No. Good news, there are many opportunities for Julia in this space. Bad news, this means I cannot cover your particular area in much depth. Great. What I will say is it's raining outside. And if you guys know, there were floods in Valencia not too long ago and floods in Barcelona not too long ago. And now I feel like I'm afraid about floods again. But that's okay. Let's keep going.
So since this talk is, fortunately or not, only 45 minutes long, and we have a lot to cover, I've added
I'm going to skip through this slide as well. We already read that slide. So we need scientists to be writing prototypes, but we already need code to be, but we also need code to be really performant. Sure. All right. Quantum ecosystem today. This is kind of where we want to start.
Today is that we're kind of in the Cambrian era of this technology. So why did I pick this analogy? In the sort of Cambrian era of the evolution of life, we went from having like not that many different life forms. Again, I don't have a biology degree, so I'm sorry if I say something that's like a little off. And then in this era, we saw a complete explosion in the diversity of life. And I saw a nice quote that said that the major forms of sort of complex animal life emerged during this era. And today we have a pretty diverse array of quantum hardware platforms that have emerged and people are actively working on, from photonics, trapped ions, neutral atoms, topological quantum computing, and the one we're going to talk about most today, which is superconducting qubits. So I don't mean that to say I think superconducting qubits are necessarily going to win, or they're best, or they're worst, or anything like that. It's just one example that I'm most familiar with that I think is sort of illustrative for the rest of the field. And the reason I think this caveat is important is if you somehow like time traveled to the Cambrian, or you look at fossils, you might say like, oh, like there's all these trilobites. Damn, these trilobites are doing really well. Like there's so many of them everywhere. I bet these guys are going to have a really great run for the next, however many billion years on Earth. And they hung out for a long time. They did pretty well. But of course, today we know there's many other varieties of life, most of which aren't trilobites. So it's a little dangerous to over-index or over-rotate on what you're observing right now, rather than trying to look forward maybe at the large diversity of platforms we have coming on stage today.
Just to pause here, I mean, there is some truth here, right? So, for example, superconducting qubits are definitely the most popular form for quantum computing now. But, for example, I know a lot more just because my PhD thesis was kind of in this area for neutral and trapped atoms, right? And photonics. I know a lot more about those. And when it comes to topological quantum computing, I don't know anything about this, but I want to learn more. Let me go ahead and catch up. Are you in Valencia? No, I'm in Barcelona. But again, with all the floods recently, it's possible that we get some flooding around here. Interesting channel and interesting group, but please try to focus on what your concrete results are in the title. Could you explain more as to what you mean? Sorry about that. Thank you, interesting channel and interesting group, but please try to focus on what your concrete results are in the title. I don't know. So the title for YouTube right now is Analog Quantum Computing. What is it, or something like that? Which is exactly what we're doing. I mean, we're learning about quantum computing, and that's the purpose. So if you enjoy it, I am glad you're here, and I'm glad that you enjoy it. If this isn't for you, I also understand that. There's a reason this is a live stream and not a standalone video. It's where I'm learning, and I'm hopefully learning together with people here, right? The point of these streams is not necessarily to like drill down heavily into a topic, though I hope that we do that. It's to have a casual conversation, talk about what I know, what I don't know, and start drilling and understanding things that I don't understand, right? And we do that together as a community. If this is not for you, I totally understand. But my hope is that people, as we start moving forward, do appreciate this and do enjoy that. For those of you guys who are just coming in, the reason we're starting with the Julia side of things is because that's also where I'm coming from. And in principle, I'd like to know what we can do, like what Julia can do in its relation to like quantum computing today. And so that's why we're starting here. I realized we did a long rant before that, but the hope is that, we go from here and then we start talking more about like what the analog quantum computing space is and stuff like that. What's becoming obvious to me right now, even at this slide, is that this particular talk is not going to be covering so much of what I'm hoping to cover. But what it will do is it will give me an idea of where the space is. So we'll watch bits of it, we're going to skip through bits of it, and we're going to try to just understand what the current state of the art is in a language that I know and I'm really good with, and then we can go from there. All your comments are cool, and interesting, but you were all over the place, my friend. Oh, for the record, Mark, I don't know if you're watching live or not. It could be in a previous point. But I will say the following. The comments kind of went through like the course of an hour or something like that. So obviously, like, there's a lot of it's not like he was talking about one thing in particular. Julia, quantum computing is super niche at the moment. Python is the de facto standard for user-turned side. I'm interested in what way Julia specifically can be better. Yep, this is also what I'm interested in. We'll see. This is just the fact of the matter is that when it comes down to using Julia today, there's always a question of why would you use Julia instead of Python? There are a lot of really good reasons for this, right, in terms of it boils down to LLVM. But in principle, Mojo also boils down in a very similar way to LLVM. So why would you use Julia over Mojo? And lots of questions like this. How about the possibility to keep coherence of quantum systems in biologically living organisms? That's a good question. So the way I currently see this is biologically living organisms are just giant, like just, phenomenally huge, especially when compared to like the quantum systems that we're talking about. So when we start talking about coherence, it's a question as to what you mean and how that, like, how could you entangle two atoms within a living biological organism? There's so many questions about how that could even happen. I'm not even entirely confident it could happen, right? All of these specific cases in which we have like hardware that is doing quantum computing, photonics, trapped ions, neutral atoms, topological quantum computing, superconducting qubits, these are all very specific cases where we have engineered qubits to exist. I don't think they naturally exist. Well, they do naturally exist in biological living organisms, I suppose, but not to an extent where they're actually useful at the macroscopic level. And so what I would say is it is quite interesting to imagine how we could be using quantum technology on biological systems, but it's very difficult to imagine what that would actually look like, right? I think is what I want to say. I did something, wasn't what I meant to do.
And trying to look forward maybe at the large diversity of platforms we have coming on stage today. So with that, we're going to dive a little bit into the sort of device physics of superconducting qubits. So one thing I just really want to emphasize early on is that many of you have probably seen a picture like this one on the right. So this object on the right is a dilution fridge. And you'll often see in the media something like this picture on the right called a quantum computer. This object is not a computer, it's a fridge. The computer is the little chip on the left there that lives inside the fridge. That's where the computation happens. You need the fridge to make the computer work, but the fridge itself is not doing computing.
I mean, I will say, okay, look, if you look at a computer and you point to the CPU, you can't point to a CPU in a computer. Why? Because it's covered by a cooler, right? I mean, this is just how it is, right? But if you were to show a motherboard to someone and you were to say the CPU is there and just point, I mean, they would see, some form of cooling. I think I agree with what she's saying. I just think it's a little bit of a moot point here, maybe a bit. But I agree. It's I guess worth saying. As with the microtubular, but maybe rather the photosynthesis pathways in plants and assumed quanta switching. Hey, there's actually some point here where like maybe this is stuff I don't know about and I'd like to learn more about. Right? Like what quantum effects actually happen at the biological level? I don't know. Penrose like quantum states in microtubules and soft hot matter is very questionable in my opinion. Right. This is also, it's not only very questionable, I would argue it's pseudoscience. It was something I wanted to talk about. I even brought up as a pseudoscience thing I want to discuss because it's very subtly hard. It's very subtle it's very hard even as a learned person to understand what's wrong with the arguments being made. Let's see, Hakumar Matata, thanks for following, really appreciate it. I mean, technically, a server rack includes cooling fans. Right. Anyway, I don't know why I paused here. I just thought she is right in saying that, like, this is a cooler and, like, everyone... But also, like, it's a bit of a weird point to make, considering, like, this is, like... It is... One of the cool things about quantum computing is how extensive, like, the cooling network is and how hard it is to actually cool it down to that level. And so I think... I don't know. I think part of the cool thing is that you have to super cool the thing in the first place. And so I think there's a lot of really cool science going in the cooling here. Anyway, let's keep going.
It looks nice, which is why it makes a great, piece for the media. But the fridge is not, it's essential, but it's not the same thing as the actual computer. So if you take one thing away from this talk, please let it be this. The object on the right is a fridge. And
One biological quantum phenomenon I know is antenna complex capturing photons for photosynthesis. That was mentioned above with 3D Prima. That means I don't know about this, and I'd like to learn more. One quantum thing I know about is for the detection of birds are able to sense the magnetic field of the Earth, and I know that there's some quantum effect here in order to allow that to happen, but I don't know much more about that. So no quantum computer on my desk anytime soon. Very unlikely you'll have a quantum computer on your desk anytime soon, unless we find a way to get, instead of liquid cooling, we have like super cooling. If that could happen and you could put that into a desktop, maybe there's a possibility, but quite unlikely.
These fridges are really amazing because they manage to allow us to store a long-lived quantum state in a superconducting circuit. And when we actually cool these chips down, they're colder than basically open space. So open space, if you measure like the cosmic microwave background, is about 2.7 Kelvin. And the fridge is actually cooled to about like 10 millikelvin. So I don't know how substantial the difference would feel to you, but to quantum objects, this difference is really significant. So this fridge, when it's working, is quite a bit colder than deep space.
Also, I'm going to pause right here. I mean, she's completely right here. I think everything she says is probably going to be right. Obviously, I'm not going to contest what she says. But it's really interesting as to how we get down into these super cooled regimes in order to do quantum things, right? This is why when we're talking about having a quantum chip in your computer, it's just so far from reality at this point that it's hard to even imagine what that would look like. I think having a quantum computer in an HPC situation kind of makes sense. A high performance computer with other supercomputing like GPUs and all this kind of stuff. Sure, this makes sense. But when we start talking about quantum computing as it relates to a physical object that you can put onto your computer, there is not currently an experimental setup that would really allow that to happen to any degree. This is why when people start talking about room temperature superconductors, this is a big deal, because if you could figure out how to do room temperature superconductors, then all of a sudden this stuff becomes possible. The fridge should fit under the desk as a PC. Okay, I mean, yeah, sure, you could fundamentally, but also the power that it draws in order to actually do the cooling is beyond what you could probably do in a home, right? Quantic Birds only works with helium cooling and some extra tricks. Yeah, so I think they're using just helium cooling, but there's obviously a whole bunch of other ways to get down to this Kelvin level, like nanokelvin. I think they're microkelvin, actually, not nanokelvin. You've got 80 laser cooling and stuff like that. Although I don't know how laser cooling works on a surface. This is actually one big advantage of doing trapped ions, in that I think you can actually cool them much lower than you can do a surface. I don't know. This is what I don't know. You don't have a 500 volt 3-phase power plug on your desk? Unfortunately, mine's 200 volt. Sorry, European power consumption. It's in the US, obviously in the US, but here in Europe, it's just not quite as good. Let me see. What do we have here? Penrose. Technically, server rack includes cooling fans. Yeah, that's true. One biological quantum phenomenon I know is antenna complex. Yeah, okay. Let's keep going.
And inside, we have this little chip that is an engineered wafer. If you went to the ASML keynote, you may remember we were discussing wafers and semiconductors. So this is a etched wafer with some sort of photolithography, and it lives inside this fridge, and when it's cooled down, it can implement some kind of superconducting qubit. And there's many kinds of superconducting qubits. There's many different architectures. So even when we...
Have you worked experimentally on a 30 Kelvin surface? That's pretty cool. I mean, I know some experiments that are in the micro and nano Kelvin. I've kind of worked with them personally, but I haven't worked with them. You know what I mean? Mine was similarly for an internship,
discuss superconducting
Yeah, pretty cool.
qubits. Just like the trilobites, there's actually many different varieties. And we're just going to discuss one of them quickly. But you should just keep in mind that there's actually a whole ecosystem, even in what might seem like a relatively narrow area of superconducting qubit design. Okay, so how does this chip actually work? So here is a relatively older, nice picture of a 4-qubit transmon device from IBM. So in this device, when it's cooled down, you have a bunch of electrons running around in the circuit. And those electrons get so cold, they pair up to form what are called Cooper pairs. So if you don't know what that is, completely fine. If you go on Wikipedia and look up BCS theory, you can learn all about what these silly little pairs are. But they only form at extremely low temperature. And in fact, for the computation to be effective, we have to cool the entire chip so much that these pairs are mostly in the qubit are mostly in their ground state. And that's why we need the really big fridge that we showed on the previous slide.
Okay, so she just said a whole bunch of things that, I mean, they're all true, but it's a bunch of jargon that I think a lot of people wouldn't know. Shouldn't you be watching news just in case there's an emergency flood incoming? My phone will go off if there's an emergency or flood incoming. I know. I won't have to worry about that. We captured our helium in a giant balloons in the basement for recycling. Pretty impressive technology. Wait, what's this? Balloons equals big sacks? Interesting. So she said a whole bunch of stuff here, and it's all true. But to be honest, even for me, it kind of went a little bit fast. So one, you cool it down to very low temperatures because my understanding is that this allows for superconduction. Superconduction is basically it's a type of conductivity of electrons through a wire where it has no resistance due to the wire. Now, the resistance of wires of the wire to electrons is basically zero anyway. Electrons basically move at the speed of light when they're going through wires. But when you cool it down, you get the option for superconducting. And when we start talking about superconduction, you can then, this is where the Cooper pairs come in. Now, this is what I need to look up because actually I don't even remember. So superconducting Cooper pairs. This is where the Josephson junction comes in, right? Am I dumb? Like, this is exactly what it does. The junction is a way in order to create a Cooper pair. Or am I wrong? I don't remember. Let's see, low temperature also reduces thermal noise. Right. Spectral bands in NV centers in diamond widen and become very noisy, but I believe they survive up to room temperature as well, as far as I understand. Diamond is uniquely rigid, so room temperature quantum computing might exist. But would it only exist? Okay, I'm going to ask a stupid question. Would it only exist in the case where you do the computation at cold temperatures and then you retain the memory as you go to higher temperatures? I'm new to your channel. What did you pursue in college? I am also in which field, if you don't mind? So I did physics as an undergraduate, but I did a whole bunch of research in plasma physics and neuroscience, just a bunch of different areas, a bit of astrophysics as well, all focusing on computational models. And then in the PhD, I did that at the Okinawa Institute of Science and Technology, where I focused on computational science of various forms, predominantly in the physics area. So I did super fluids and stuff like this. Right. So let me just kind of remind myself of how the Cooper pairs work, because even in my classes where we were talking about quantum information, it was mostly theory, right? We talked about Brockett notation, stuff like this. We didn't talk so much about the experimental implications. It was there, right? Let's see, Cooper pairs disassociate on high temperature, so all confidence will disappear with that. Yeah, I think my question was related to Evgenie's comment above about NV centers. Why work at ANSYS. I don't know what ANSYS is. Otherwise, I guess I might work there, but I don't know what it is. So I don't know. Maybe I don't like those people. I have no idea. So in condensed matter physics, a Cooper pair or BCS pair, Barden-Cooper-Schrafer pair, is a pair of electrons bound together at low temperatures in a certain manner, first described in 1956 by American physicist Leon Cooper. Yeah, so Cooper is a very interesting person who I know his work not necessarily because of the Cooper pair. I know his work because he actually went into neurophysics after this. And I somehow managed to find him because of that. And then randomly also noticed the Cooper pair. Okay, so relationship to superconductivity. I think this is what I want to read. The tendency for all Cooper pairs in a body to condense into the same ground quantum state is responsible for the peculiar properties of superconductivity. So superconductivity is very similar to superfluidity in a lot of ways, but I don't remember all of the analogs here. So Cooper originally considered only the case of an isolated pair's formation in a metal. When one considers the more realistic state of many electronic pair formations, as is elucidated by the full BCS theory, one finds that the pairing opens a gap in the continuous spectrum of allowing energy states of the electrons, meaning that all excitations of the system must possess some minimum amount of energy. This gap to excitations leads to superconductivity, since small excitations such as scattering of electrons are forbidden. The gap appears due to many-body effects between electrons feeling attraction. That did not totally explain anything to me in any way, shape, or form. I gotta be honest, my physics brain has been off for years. I don't remember this at all. I'm an undergrad right now, just studying about these in solid state physics. Cooper pairs, hey, explain it to me. Actually, Please don't redact that message. I saw that message. Explain it to me. I want to learn more. I've forgotten all about this, like everything about this. I've completely forgotten apparently. So you undergraduate, explain it, please. So my question is the following, right? I know that these pairs must form qubits, right? And so I have no problem with the electrons entangling or what is the bit in this case? Like what part of what is the bit, right? That's my question, I think. Electrons in a pair are not necessarily close together because the interaction is long range. Paired electrons may still be hundreds of nanometers apart. That's fine. This distance is usually greater than the average inter-electron distance, so many Cooper pairs can occupy the same space. I probably shouldn't have read the middle paragraph. I probably should have read another paragraph first, but hey. Although Cooper pairing is a quantum effect, the reason for pairing can be seen from a simplified classical explanation. An electron in a metal normally behaves as a free particle. The electron is repelled from other electrons due to negative charge, sure, but it also attracts the positive ions that make up the rigid lattice of the metal. This interaction distorts the ion lattice, moving the ions slightly towards the electron, sure, increasing the positive charge density of the lattice in the vicinity. This positive charge can attract other electrons. At long distances, this attraction between the electrons due to displaced ions can overcome the electrons' repulsion due to their negative charge and cause them to pair up. Okay, the rigorous quantum mechanical explanation shows that the effect is due to electron-phonon interactions, with the phonon being collective motion of the positively charged lattice. Are Cooper pairs what causes Bose-Einstein condensation? This is quite different. So Bose-Einstein condensation is in a sense much easier to understand. It's literally just a bunch of bosons that you cool down to, nanokelvin-ish regimes. And when you get down to that stage, what ends up happening is that the ground state of all of these particles are at the same location, roughly, which kind of causes them to create this goop, the superfluid goop, where they're all superpositioning at the same spot at the same time. So it's, okay, I'm not going to say it's easier to understand, but at least I kind of understand how that happens. You answered the question. Live stream is experimental, and so I'm hanging in there, especially since I know you studied photonic computing. It isn't just obvious, go bosons, drop fermions. Yeah, so wait. Isn't it just obvious go bosons, drop fermions? So this is the thing. It's been so long since I did anything with bosons and fermions. Like I've been so far removed from the discussion of any type of physics that I am not the person to talk. I can learn this probably pretty quickly, but I've forgotten most of it. Does the Wikipedia article cite the original article about Cooper pairs? I hope so, right? Must be this one. PDF? Can I just download it? Let's see what we got here. Open that bad boy up. It opened on Firefox, which is fine. Let's see what we got. All elementary particles are fermions. No. No. What do you mean elementary here? Or maybe it cites a summary article on what Cooper pairs are and applications of that model to understand various systems. Yeah, so let's see what it says here. Except for force carriers. To be honest, look, I'm going to be honest. I'm a bad physicist. I've always been a bad physicist. I kind of only really learned enough physics to do computation. So when you start talking to me about like things I should know, like, like elementary particles and stuff, this is all stuff that kind of goes in one ear and out another with me. It's not necessarily that it's not interesting. It's just not like, it's not where my interest is all the time. And so I find myself struggling to remember like all the details here. So this paper is literally just 2 pages. No way, right? That can't be true. I mean, if it's just 2 pages, let's just read the whole thing, man. Let me open this up in Zernal PP. Zernal PP, PhysRev. Now this is where, must be .104. All right, pop this bad boy up. Okay. So we're going to go here, open access, but bosons and fermions are defined by their spins. So parallel electrons form bosons as their spin is 1. Is that true? Yeah, I guess that's true. Yeah. I'm really out of the physics game, guys. I've completely forgotten how all of this works. It's been proposed that a metal It's been proposed that a metal would display superconducting properties at low temperatures if the one electron energy spectrum had a volume independent energy gap of order of something Kelvin temperature between the ground state and the first excited state. We should like to point out how primarily as a result of the exclusion principle, such situations could arise. Consider a pair of electrons which interact above a quiescent Fermi sphere with an interaction of the kind that might be expected due to the phonon and screened Coulomb fields. Okay, lots of things here that I've forgotten. Quiescent voltage. Quiescent as in quiescent voltage, I feel is different than quiescent Fermi sphere. I feel like these are two different things. So I need to, both on like quasi-particle makes sense. I understand some of these words. Yeah, this is exactly where I'm at right now. Does it actually matter? Maybe not. Maybe we can kind of keep going from this point and we can just kind of ignore some of this. And we can just say, yo, look, given the fact that these superconducting circuits, the superconductivity allows for electrons to couple, and that coupling allows for, qubits to exist. I guess we could just say that as a statement and keep moving, because we don't necessarily need to understand all the physics here, but it is a little bit disappointing that I can't remember any of the physics, right? So maybe I should just Google Josephson junction, and that's where we should start, because I feel like this is related. Joseph. Come on. And admittedly, another problem here is that I don't really intend to understand like digital quantum computers so much here. My goal is actually to understand another type of system entirely. And so this is really just a way to more accurately like figure out what the state of the art is and then go from there. This might be too deep in the weeds. To be fair, it shouldn't be too deep in the weeds. I, as someone who learned physics and did this in class, should be able to tell you right now how this works. But I can't because I've forgotten all of it. So yeah. Are you going to write a numerical solver for this stuff? No, my goal isn't to write a numerical solver. My goal is just to understand how this works with the hope. So I actually have a conversation with the CEO of one of these companies who is doing analog quantum computing in the next week or two. It's not necessarily a business meeting, but I do kind of want to understand where their research is coming from so that I can more accurately understand where I could potentially help if they needed help in the future, right? That's kind of where I'm at. And obviously I could just ask them questions, that's fine, but I kind of would rather see if there actually is any way forward first. Like, is there some potential where I could use my knowledge of Julia and GPU stuff in order to create like some better hardware integration with quantum devices? Is that possible? I don't know. That would be interesting. And it would certainly be interesting to look at. Even on stream, it'd be interesting to look at if we could find some sort of like mid-level IR for quantum devices of a particular type. I don't know. This all sounds really cool, right? I remember all of my physics. Hey, you're much better than me. I've forgotten all of it, like literally all of it. I only remember what I need for my specific project, and then I have to refresh myself every time. So in physics, the Josephson effect is a phenomenon that occurs when two superconductors are placed in proximity with some barrier or restriction between them. The effect is named after the British physicist Brian Josephson, who predicted in 1962 the mathematical relationship for the current and voltage across weak links. Okay, it is an example of macroscopic quantum phenomenon where the effects of quantum mechanics are observed at ordinary rather than atomic scale. The Josephson effect has many practical applications because it extends a precise relationship between different physical measures, such as voltage and frequency, facilitating highly accurate measurements. Cool, this all sounds great. The Josephson effect produces a current known as a supercurrent that flows continuously without any voltage applied across a device known as a Josephson junction. This consists of two or more superconductors coupled with a weak link. The weak link can be a thin insulating barrier known as a superconductor insulator, superconductor junction, or SIS. In short, a short section of non-superconducting material, SNS, or a physical construction of that weakens the superconductivity at the point of contact. So, okay, this to me is like a capacitor. So for those who don't know what a capacitor is, it's essentially it's a bit of electricity, it's a plate, a metal plate, and then there's like an insulator and then another metal plate. And what this is useful for is in many circuits, you can use a capacitor as a way to kind of Gosh, guys, my analog electronics, I've forgotten everything. What even is a capacitor useful for? It's kind of like you've got, everything is out of my brain, isn't it? I can't even remember. What it does though is I remember there's like an oscillation that happens between the electrons when you have a capacitor, right? Like the charge will build up on one side and then it can't pass, so it builds up on the other side. I vaguely remember this happening. Yeah, buffer current, I vaguely remember about this. Yeah, LC currents. Let me Google LC currents. Circuits. It capacitates. Thanks for that. I'm not 100% sure on where you're going with this. I thought Josephson junctions were like related to capacitors. Like they were basically the same thing, just for superconducting circuits. But maybe I've completely forgotten. Resist charge and voltage. How many degrees of freedom axes does a qubit have? I'm thinking on those 3 blue 1 brown videos where high dimensional vectors have a very low likelihood of having substantial cosine similarity. And this being useful as a model for machine learning in terms of representing dispersed notions. Let's see. To be honest, it really depends on how you want to read the qubit. There's like this entire block sphere that the qubit could exist on. And so it could measure like literally anywhere within a 2D surface. So I guess the answer is 2 degrees of freedom. But this depends on how you do the measurement. So I don't know if that's necessarily the answer to your question. All I remember is something with a condensation of electrons. It capacitates. Let me just go here. So LC circuit. Right. An LC circuit, also called a resonant circuit or tank circuit, is a tuned circuit, or tuned circuit is an electric circuit consisting of an inductor, represented by the letter L, and a capacitor, represented by the letter C, connected together. The circuit can act as an electrical resonator, an electrical analog of a tuning fork, storing energy oscillation at the circuit's resonant frequency. Let me look at a capacitor. Let me just look at a capacitor. I don't remember. I've forgotten everything, guys. In electrical engineering, a capacitor is a device that stores electrical energy by accumulating electric charge. Yes. So I understood that. I remember that. On two closely spaced surfaces that are insulated from each other. The capacitor was originally known as a condenser. It's probably not enough degrees of freedom for that phenomenon. Yeah. So let's just keep going here. There's a lot of stuff that I've just completely forgotten how it works. Apparently, I took analog electronics twice actually. One as an undergraduate and another as a graduate student. And I remember being quite good at it. I remember being like, yeah, this is really cool. And even when I started doing quantum computation for the first time, I was super into SPICE circuit models at the time, which is how you do a lot of these analog electronic circuits. It's like a particular formalism for talking about analog electronics. And I remember in that space, I created the QSPICE code base, which was a quantum spice. It was basically a way to draw quantum circuits as opposed to classical circuits. So I remember being like really into this kind of type of stuff, and now I'm like completely, this all is new to me, you know. So let me see what we have here. I think what we're going to have to do today, guys, we're going to have to come back to this because I do want to get through the Julia talk right now. So we're going to have to come back to this and talk a bit more about this later on. And this might be something I need to just remind myself of off of stream. But this is certainly something that I want to come back to, and I want to just learn about, like how these digital quantum computers work. But for now, I just want to know where we're at, what we can currently do with them. And I think it's best just to go through the talk and come back to this a bit later. That's where I think we're at. I recognize that for the first stream where we're doing this kind of like, more or less just learning together type of thing, I recognize it's kind of not exactly streamlined, but that's okay. The first stream will never be streamlined, and we can kind of go from there. So let's keep watching this, kind of go through what we need to go through, learn more, and go from there. It's probably not enough. 1 axis for each qubit, so as much dimension as you need. Block sphere is actually a hypersphere. Oh, I didn't know block sphere was a hypersphere. Is it a hypersphere? Oh, that's new. I thought it was just a 2D surface, but I didn't realize it was a 4D surface. The most you can get is like tens of qubits, the thousands or millions you'd need. Right. Okay, so let's keep going.
So without the fridge, none of this works and we can't do any computations. And then on the chip, you can see there's 4 little traps, and we make an idealization that within the trap, there's either 0 pairs or 1 pair. So that's called like a charge box qubit. And this transmon design that they have here actually does something even more sophisticated to make these pairs, or the states that represent 0 and 1, longer lived. But that's effectively the bare bones description of what's going on here. So we trap these little pairs in these 4 regions, and we can say there's either none of them or 1 of them. And that lets us do computations with them. And we manipulate them with the wires you can see on the outside of the chip, So we have all these wires that are connected to the external environment, and we send microwave pulses through the wires to control the device and do computation. Awesome, wonderful. Now we're computing. Great. So this would be, we'd be ready to go, except of course, when we're controlling the device, it's not isolated. So if the device were completely isolated and we never had to talk to it, these quantum states would be super long-lived. And everything would be great. But for us to do computations, we have to interact with the device by controlling it and then initializing it and reading it out. And this introduces a lot of potential for...
Yeah, I saw the bracket notation as well over here. And it's like, man, it's kind of like it brings back memories of a life I lived in the past. And it's like, man, it's been a long time since I really legitimately thought about this type of stuff. Yeah, I've got to learn a lot if I actually want to do anything with quantum. Everything's been forgotten.
For things to go wrong. So we're kind of trapped in this annoying dilemma where we want the device to be totally isolated up until the exact instant we want it to do something. And then it has to become unisolated, and then we need to isolate it again really quickly. So the entire sort of dilemma that we face when designing these devices is that we have a lot of trade-offs to make. So we have to draw a layout for these wires and these qubits, and then again, as we saw in the wonderful ASML keynote yesterday, we have to actually create the chip, which is itself a very complicated process. Using that layout we drew, we put the chip in the fridge, great. We cool it down, we run our workloads, see how good they are. Usually they're not so good. And then we improve steps 1 to 4 by gathering data. Okay, so we're going to discuss steps 1 and 4, because those are the ones that are probably most relevant here. But if you want to know more,
Okay, I don't understand how muting works, guys. I tried twice to unmute myself, and somehow I failed. I think it's just my key. Thank you, guys. I appreciate you telling me I'm muted. I'm not muted now. I'm pretty sure you guys can hear me. So here's what I was saying. Bracket notation, something you only see in physics. It definitely gives people... Guys, I'm not muted. I appreciate that. Thank you so much for telling me. I do appreciate it. I literally was like... So I muted myself. I tried to unmute myself, but only whatever. Anyway, fine. Point is the following. Oh gosh, I've even forgotten the train of thought now. I don't even remember what I was going to say. But thank you for telling me I was muted. I appreciate that. And I was muted twice. Doubly embarrassing. That's fine. Right. Bracket notation is really only used when we're talking about like quantum information and stuff like that. So it's definitely something that like it's quite useful. It has a lot of variation or a lot of utility here. But like even in quantum systems, you don't see it that often. Like the simulations that I used to do. But what I was going to say was something related to something that she was talking about, and I just completely forgot what that was. So I'm going to have to mute myself. I'm going to have to listen some more, and then we'll talk some more after I remember what that was. So sorry.
About 2 and 3, or especially 2, you could probably find someone from one of our awesome sponsors, ASML, and learn more than you ever wanted to know about wafer deposition. So when we created a device layout, we have a bunch of trade-offs we have to make. And this is true, of course, in classical chip design, but it's true in quantum as well. So one of the big ones is the fridge we're thinking of has a fixed size, and it's really not very easy to expand it. So we got to get the chip to fit in the fridge die. And we want more qubits on the die, because that will let us do more computations. But we have to be able to address and control each one of those qubits. And
I'm not gonna like judge. I mean, this person, like, she's clearly giving a great talk. I appreciate the comments, but how am I supposed to? Okay, so I have to do these QR codes now to see what she's talking about. All right, let's see. Sorry about this. I just gotta. So what is this? This is software for at ASML, the force behind making microchips. Okay. Oh, these are other JuliaCon talks. I gotcha. And that one is computer-aided design of quantum integrated circuits. This one is also a JuliaCon talk? No. It is these are other, these are both Julia things. So the first is, how do I give you guys these links? How am I going to do this? So computer-aided design of, so the first one was layout.jl, which is here. Graphics layout manager for Julia. We present layout.jl, a package for computer-aided design of this of superconducting quantum integrated circuits. Intended experiment with graphical layout management in Julia. I feel like this is quite different than what they were talking about on this. Layout.jl is a package developed at AWS Center for Quantum Computing. No, this is a different thing entirely. One second. Quantum G? I can't find this. Are you guys able to? How do I do this? I need to give you guys this information. So, computer-aided design of quantum integrated circuits. Nope. Julia. QR codes with very clever and useful. Please stop using them for everything. No, I think what I was hoping for, it's basically impossible for there to be a solution here. I was hoping for a link. Like, I just wanted, like, an article to look up. But I think what ends up happening is they will send me to other JuliaCon talks, which I don't necessarily want to look at right now. So I think what I'm going to do is I'm going to, like, scan these QR codes and see if there's, like, something that I think we should share. Otherwise, we'll keep going. So the other one was software at ASML, the force behind making microchips. So I don't think either of these we necessarily need to talk about. One is for a CAD design for superconducting quantum integrated circuits. I think these are just mentions of things that you can do in Julia. So I think, we're okay to keep going.
And the more components that are close together on the die, the more potential we have for quantum interference effects, for all kinds of errors to be introduced. So we have this odd sort of trade-off we have to make where we have something of fixed size and we're trying to cram as much stuff into it as far apart as possible, in a rough sense, which is pretty problematic. And that's something that we can do computationally, and it's something where we need a lot of very high performance simulations running quickly many times per day. So how do we actually do this? When we come up with the layout, we don't stand there waking up from a dream and just draw something, or maybe some people do. But usually what folks do is they say, okay, luckily we've been studying electromagnetic physics for a long time. We have a pretty good idea of how both.
Yeah, actually, for me, I like archive links. So I think if your QR code is on like somewhere, like you should also just write like the archive, like number code associated with that, so that we could find that. So this is, I probably want to read Zhang et al. 2023, and I just want to see what this GitHub repo is. So let's see, the GitHub repo is going to be for, it's not loading. Let's go back over here. Okay, so a scalable superconducting quantum simulator with long-range connectivity based on photonic bandgap metamaterial. This could be interesting to look into as a paper, and then we have, I've got to find the other one, the Palace GitHub repo. See if I can find this guy. 3D finite element solver for computational electromagnetics. I guess I don't fully understand what these are for. So
quantum electromagnetism works. So what we'll do is we'll first draw some layout of the components we want on the chip. And then first we do a classical EM simulation of the circuit, which has a bunch of nonlinear elements. So effectively here, you're doing some sort of finite element simulation, and there's a lot of nonlinear pieces that go in there. This is, as many people can tell you, a very computationally difficult problem. And for every single layout you want to do, you've got to do this first to make sure, effectively a sanity check, like even without considering any quantum effects at all, is this feasible? And then once you've done that, okay, looks good. You do a Hamiltonian simulation that involves the sort of purely quantum physics that combines the classical results you got in the previous step with quantum effects. So just to shout out quickly to some of my colleagues.
Yeah, so this, I actually want to learn more about the Hamiltonian simulation. I feel like, when you talk about quantum computers and stuff like this, a lot of people say you're really solving a Hamiltonian, which is true, it's a true statement. But it's interesting to me to, I want to see what that means, you know? You probably want to model photons, or possibly more generally boson quasiparticles, as waves using Fourier transforms. My man, Julia Fourier transform are n-dimensional and butterfly Fourier fast. Wait, I might have missed something here. I'm not entirely sure how it's related to Julia here or something, but tell me more. I'm interested in your take, what you were talking about. Just like explain it more thoroughly in a way, and I can probably understand it more. Guys, I do have to be a little bit honest here in saying that I got to go in like 25 minutes. So what I'm going to do is I'm going to kind of flip through the slides, and I'm going to see what they're talking about, see if I can just kind of understand it from my own perspective, and then we go from there. I realize I'm butchering the talk, and for people who are here and they're kind of enjoying and vibing with the talk, here's what I'm going to do. The talk is available online. Let me just give you guys a YouTube link right now. Here you go. Copy this bad boy. We're going to paste it there, and we're going to paste it here. You guys can take a look at that on your own time. But for now, I do want to get through the talk because it is a little bit off the beaten path of what I wanted to go into. So I'm hoping to finish it up in about 20 minutes, take about 5 minutes to talk about what comes next. So, okay, let's keep going. So right now, low-level calibration of the device. Apparently, you wake up in the morning ready for another beautiful quantum day. You run experiments to check qubit quality. The qubits look good. Run a bunch of workloads. As you run programs on the chip, it begins to drift. After some time, rerun the quality experiments and adjust to keep the device at acceptable quality. So we have quantum-control.jl and piccolo.jl. Let me see what these are. What's going on? Piccolo.jl. Here we go. Should be okay. This is probably what I'm looking for. A convenient meta package for quantum optimal control using the paid integrated collocation method. Yeah, okay. Gotta be honest. I think somehow I'm lost. And I get lost very easily, and I understand that. But how did we get to quantum optimal control? Okay. And then the other one here is quantum control.jl. Which is here. Is a Julia framework for quantum dynamics and control. Attempts to steer quantum systems in some-desired way by finding optimal control parameters or control fields inside of a system Hamiltonian or Liouvillean. Typical control tasks are the preparation of a specific quantum state or the realization of a logical gate in a quantum computer. Chip design and optimization. Right. I get that it's chip design, but but what are we optimizing, I guess is the question. On the paid integrated collocation method, what is this? Direct collocation for quantum optimal control. Yep. What do we have here? Kestrel quantum. It looks to me like we present an adaptation of direct collocation, a trajectory optimization method commonly used in robotics and aerospace applications. Okay, to quantum optimal control. We refer to this as the paid integrator collocation. This approach supports general nonlinear constraints on the states and controls, takes advantage of state-of-the-art large-scale nonlinear programming solvers, and has superior convergence properties compared to standard approaches like grape and crab. Oh, I know grape and crab. I know what we're talking about now. I gotcha. Totally understand. Pico also allows for the formation of novel free time and minimum time control problems, crucial for realizing high-performance quantum computers when optimal pulse duration is not known a priori. We demonstrate Pico's performance on both the simulation and hardware with a 3D circuit cavity quantum electrodynamic system. Okay, good. I think I understand what's happening now. So quantum optimal control, I did this way back in the day at the start of my PhD. It is basically using optimal control. Think something like gradient descent on a system of Hamiltonians in order to basically create an ideal state at the end. And so essentially you have a goal state that you're trying to get to. This could be like a connection between qubits or something like this. In my case, I was trying to essentially create a particular... I don't know how to put it. We were trying to create a particular state in this like ring of atoms going around... basically a ring of atoms in what's called the Tonks-Girardio gas, which is a strongly correlated gas. Point is, we use this particular technique in order to like create a specific eigenstate, to say, how do we go from point A to point B? What is a time evolution to go from point A to get to the state that I want, right? So you have some goal state that you're heading to. And then the question is, how exactly do we shake the system up in order to get there, right? That's what I know about quantum optimal control. Now, can you fill us in too, now that you're no longer lost? So I understand, I now know a bit about quantum optimal control, but the thing I don't understand is how this is related to, is this just another package? Is that what this is? It's just another package. This looks like another package using classical computers to simulate quantum systems. I think that's what this is. We are transpiling a high-level quantum circuit into our real gates and chip topology. Is it a real system or is it a simulation? I thought this was a simulation. Let's take a look at the PDF. I really understood this to be a simulation. But maybe not. Let me see what they have for experimental results. What is this? So Pico pole simulated state evolution for target state, G1. Time evolution of the separate transmon. Do they have physical results? These don't look like actual... These, to me, seem like simulations over a physical device. So I might be wrong, and I probably am. But to me, this seems like the invention of a new quantum optimal control technique as opposed to actually being used on quantum hardware. That's to me what I'm understanding. And again, feel free to tell me I'm wrong. I could be. And I'm more than willing to talk about this, obviously. That's why I'm here, right? Okay, so let me take a look. Oh, quantum control. Okay, this is also in the framework of quantum optimal control. Good, I understand now. Gotcha. Okay, let's keep going. Again, I'm going to flip through the slides, and you guys are just going to come back and tell me in the comment section, yo, you actually didn't understand anything, and that's okay. We'll come back for another stream. I got to kind of flip through these pretty quickly. So we'll get through these and figure out what's going on. Bye for now. Got to go to sleep. If there's any discussion about AI copyright, I won't be here. Oh, hey, Hanif, thanks for being here. I will say the following. I don't know if you're still here in chat. The AI copyright discussion will happen sometime. I'm not sure when. It might come later this week, but I want a dedicated stream for that because it's very complicated and there's a lot I want to learn and I want to talk about. Okay, classical simulation of device operation. Yes, this is exactly what I was expecting to happen. Good. Let's keep going. I'm just flipping through. So programming the device, circuits, and gates. Yes. So again, this is just showing that it's possible to do the simulation on classical computers. What is a quantum gate? Again, we don't necessarily need to talk about that right now. For now, we can kind of see it as a black box that does something to a quantum state. There's a lot more about this, and actually there's some really good papers on understanding how quantum computation happens. The reason I don't want to go so far into this is because my goal is to understand analog quantum computing, and this is very much a digital analogy and not the analog one that I want to get into. So this is something that I'm hoping we will probably talk about if people are interested. And of course, I've done my own quantum circuit simulation before, so it's not like this is brand new to me. I'm vaguely familiar with this. Someone, the past James, somewhere in his past life, did this before. So it's certainly something we could talk about, and I think it's worth talking about. But for now, I think we just keep going. Implementing gates on real devices. So to actually implement quantum circuits, we need a series of microwave pulses through control wires. What's the optimal pulse to implement a certain gate? Yes, perfect. This makes sense. This is why you want to use optimal control, because it allows you to figure out that optimal time series in order to figure out how to get that gate to work. Gotcha. So again, quantum optimal control is the process of creating a particular quantum state with some particular time evolution, right? How do you get to the state that you want? With that said, it makes sense that you want to use this for the device, and now we understand how this is related to hardware, exactly as Evgenil said before. They might be doing just simulations in the paper, but the hope is that this is directly related to hardware. Gotcha. Ooh. Representations of quantum programs. Just as we have many hardware options, we also have several intermediate representation options. This is what I want to know. A new experimental pure Julia open QASM3 parser based on autonoma.jl, written by me, needs help with open pulse. So let me look at, looks to me like we have some sort of assembly, quantum assembly, QASM3, and open QASM3. So this already answers my question. With relation to, is there some sort of middle-level intermediate representation for quantum devices? It sounds like something like this is kind of in the works, but it's really just at the assembly level. We don't have that mid-level representation just yet. I want to look at Quasar. I assume these are all kind of similar. OpenQASM, QIR, and Quasar.jl. So let me take a look at Quasar.jl. And let's see what we can find. I want the GitHub repo. How do I get to the GitHub repo? 1 second. Docs. There are no docs. Of course there's no docs. What was I thinking? Source code. I knew it was that button, but I didn't see the GitHub logo, so I was confused. Quasar.jl is a quantum assembly lex parser, is a package for lexing and parsing quantum assembly. This is perfect. That's what I wanted to know. There is some sort of assembly that can work on these devices. Now, I do kind of wonder if this is general for everything. Like, does this work on analog as well as digital? I don't know. I think not. Quasar.jl works in a two-step fashion. First, it uses a tokenizer to generate an abstract syntax tree representing the quantum program, which is a nested structure of QASM expressions. Good. Then it walks and visits the ST to evaluate all loops. This seems pretty cool. Yeah, so we have the QASM gate. Good. Okay, so what this looks like is, it looks like QASM exists, and this is a way to parse it within Julia. Perfect. This is all stuff that I was hoping to see. I'm glad I saw it. Representations of quantum programs. Why? Unfortunately, we might have to skip through the why. Cleaning up all the abstractions, additional abstractions such as computation of gradients, measurement optimizations, mid-circuit measurements. One program may become thousands of instruction sets. Fair enough. Then there's Yao.jl. I've been wanting to learn about this one. So Yao.jl is an extensible, efficient, I was just reading what it says, and now is an open source framework that aims to empower quantum information research with software tools. It is designed with the following in mind: quantum algorithm design, quantum software 2.0, quantum computation education. So installation, Yao is a Julia package. To install Yao, please open Julia's interactive session known as a REPL and press this and do Yao. Sure. There's a tutorial. Maybe this is something that we look into. Actually, in fact, if you're interested in doing quantum computation with Julia, just let me know. And maybe this is something we look at in one of the future streams. This is definitely something I'm interested in, and I want to learn how it's done. So yeah, it looks like they have Grover's algorithm in here. And Shor's, do they not have Shor's? Maybe it's just Grover. So yeah, this might be perfect to go through so we understand more about quantum computation. Good.
Some algorithm that I heard about from...
Oh, let's just skip through because, again, I'm running out of time. Accounting for device topology. This is interesting, and I think it's worth looking at, but again, I'm running out of time. So some hardware types are all-to-all. Yeah, but I don't think we have any hardware types that are all-to-all. But superconducting devices have a definite layout. So this is what I was saying before. Yeah, I'll throw some links in the chat in just a second. In fact, let me just go here and let me just paste Julia Basics, setup environment, quick start. Let me just go back. I'm just going to post this in chat over here. So this is a Yao, and this is Yao. Okay, let's keep going. So this is what I was saying before. Really and truly, we don't have like a universal quantum computer that exists. Like all these superconducting qubits are like nearest neighbor, which is good, but not exactly what people want all the time. Good. Let's keep going. Again, I'm just going to skip through the slides, and then we'll talk about things to do from here. So, quantum devices are subject to errors. This is true. This is why we talked about error correction. It's so important. Let's see, quantum devices, let's see, with noise, without noise. This is basically just talking about how bad the error is. And note that it's like, lots of occurrences of different, so this is like maybe a 25%. So with 15% bit flip noise and stuff like this. So essentially what they're saying is the noise is a big problem that we have to overcome, which is why a lot of people have been talking about like quantum error correction and why this is so important, all this kind of stuff. Coping with a noisy world, experiencing unwanted X gate ride-alongs, just say no. It's illegal to flip a qubit without your consent. Okay. We can mitigate the effect of an error. We can suppress the errors with real-time adjustment of our pulses, or we can correct the errors. So then there's a lot of papers in here about how to do that. This one's probably something I want to look up, actually. 1208, 0928. Surface codes towards practical large-scale quantum computation. Hey, this is actually a very good thing to look at. And again, let me know in the comment section if you want to see this in the future. Surface codes towards practical large-scale quantum computation. This sounds perfect to look into. It seems to me like it's exactly asking, and in fact, maybe this is even linked earlier in chat. It's asking how do we actually start building large-scale quantum computers, hopefully at a theoretical level, but even and touches on how to do that experimentally. I'm going to keep going. Whirlwind of 2-hour surface code. We're going to have to skip through a lot of this. It's not just error. Quantum devices are also subject to defects. Yep. Healing dynamics defects. Yep. This is all stuff we need to talk about, but I don't think we can necessarily do that today. Defect detection and healing is complex. Classical simulation of quantum algorithms. Good. Yep. This is all quantumoptics.jl. This is all stuff I know about. So basically these are, ways in which you can use Julia or other toolkits to do quantum simulations. For Python, there's also, what's it called? QTIP, QUTIP, which is used for this as well. Quantum chemistry. Okay, this is all stuff. Quantum chemistry with quantum computers. So this is something I want to learn about because I didn't actually know. I don't know the utility here, so it's certainly something I want to learn about as well. Let me go ahead and just modeling carbon capture on metal organic frameworks. Modeling carbon capture quantum. See if I can find this bad boy. This guy is the one I want. Okay. Which geometry will nature favor? Good, good. Translating continuous systems to qubits. Yep. This actually might be what we want to look at as well for when we start talking about analog stuff. Like how exactly do we take an analog and system and turn it into something that we could do digital operations for? Like how do you implement Shor's algorithm on an analog quantum computer? I don't know. This is tough to talk about. Unitary coupled cluster, singles and doubles, scaling integers. But this is all the stuff that we want implemented. Noise, VQE, all this kind of stuff. What are we waiting for? Integer factoring. What are we all waiting for? Integer factoring. Yep, this is what we talked about before, how there's really only 1 or 2 good algorithms, and this is one that like we do really care about. So to factor 496-bit keys, you need 1000 logical qubits. Today we have 1. Yes, that is exactly how it is, right? We need way more qubits. Yep, good. So good they commented on that. So Julia's role in a quantum world. I want to read this slide. Opportunities today to contribute at all levels. Check out our sponsor, Unitary Fund, and community team Quantum Savory for microgrants and project opportunities. Maybe if we do want to continue doing quantum stuff, it's worth looking into these grants. Can't assume quantum computing will evolve as classical computing did, and the Julia quantum community is diverse and growing. Okay. Lots of stuff here that we could talk about. What I'm going to do is just kind of write it all down, just so I have an idea of what we're talking about here. So let's go back over here. Journal, new page before. Let's start with the interesting thing. So one, we went into this discussion with a question. We were talking about what the question that I was hoping to answer today is, what is analog quantum computing? We did not do that. Just for the record, we did not do that. I apologize. We rambled for a lot. But what we did do is a lot of different things. So one, we talked. And again, I said before, and I will say again, that this talk is very important. It's really, really important to have just discussions at a technical level about things that are technical topics that people care about. And so talking about GPU, talking about machine learning, all this kind of stuff, there's all these things that we could talk about in the future. And there are things that we will talk about in the future. For example, AI and copyright. This was briefly brought up earlier in stream, but it's something I want to talk about. And really AI at all levels, like, just things that we were talking about before, like, I don't know, just a bunch of different machine learning stuff. So like, there's a whole bunch of things here that are in the paper pile in Discord. Feel free to check that out. Lots of things to talk about there. GPU is another thing that we're definitely going to be doing a stream on. Julia's role in GPU is also in there. So let's talk about quantum. After that, we had a long discussion, probably 2-hour discussion about different things that people were interested in. Then we started hammering in about quantum. And what we did is we talked about Julia in quantum computing. Now, to be honest, we flubbed a little bit while we were talking about like how to actually watch the video on stream. My bad. From now on, I know I'm just going to YouTube download everything if we have to watch it on stream. And also in my defense, I was not expecting to watch a video today on stream. It's just that just before stream, I was told about this video and what to watch. So what do we know? So let's start talking about what we know. So one, Julia can be used in a bunch of different ways. It can be used for simulation of quantum systems, right? So this involves a whole bunch of different things. So we'll say quantum optimal control is a good thing here. We'll talk about anything with quantum optics. .jl, that's great. But another really interesting thing here is QASM, which is the quantum assembly, and I think it was called quasar.jl, which is a package used in order to translate the quantum assembly, which is something that's needed to do the like talking to quantum devices, right? And as someone who has been interested in the analog computing question, because these are the people I'm going to be talking to physically, I'm very interested in, is this actually useful? Is this useful for all architectures? Or is it really only for like superconducting qubits? I think it's just for superconducting qubits, but that's my question. Is QASM useful beyond like for all the other methods, right? Okay. See, there's a whole bunch of other things that we talked about, and I can go ahead and just briefly remind ourselves of this. So modeling carbon capture on metal organic frameworks with quantum computing. This is an interesting question, right? What can a quantum computer do better than a classical one? That's a question. I don't have the answer to that. Is it, there are certain models that I know you can do, like chemistry models, but can any quantum computer do that? Or is it just like this particular set? Like there's questions here. I want to learn more about places where the quantum computer can actually flat out beat classical computers and when that happens. Don't forget quantum AI and quantum crypto. Actually, we might put something in there. So pseudoscience in there. Okay, what else do we have here? Other things that are interesting. We have towards practical large-scale quantum computation. How do we scale? So down here, we're going to say, how do we scale a quantum computer? That's a question. And also in here, I'm going to put different types of quantum computers as well. Different types of quantum computers. Computers. There we go. And in here, we're just going to capitalize that for fun. There's a bunch of other stuff that we could talk about. The Yao tutorial, I think, is another thing here. F would be the Yao tutorial, if I could spell it correctly, which I cannot. All. And what else do we have here? Let's see. Quasar, talked about that already. Quantum control, we already talked about this. Good. Okay. So for the record, I know I have to end the stream basically now. I got to go pretty soon. But we talked about a lot of stuff. And this is very important. Having these discussions is the core reason I'm streaming, right? Sure. The amount of research that I did in the past 4 hours is negligible. I 3 hours and a half. I did not get that much done. But I think part of the reason I'm streaming now is not necessarily to get a lot done, it's to do as much as I can with the community. Because I think even if I'm slower at research, I'm slower at getting things done, I will still be accomplishing something beyond just doing the research alone. Like I've said many times before, your research is only as good as your ability to communicate that research. And so here I am trying to do research live. And I'm hoping that people who are watching the stream, either in the VOD or watching it right now, understand kind of the vibe I'm going for here. It's literally just us learning together, right? I've tried this before many times, but this is the first time I'm like literally just going for it. I'm just going to see what people say. And like what Akras is saying in chat here, part of the goal and part of the struggle when you're learning together in this way and you're trying to learn things for the first time is one, you forget a bunch of stuff. I've forgotten a heck of a lot of physics that I should still remember. But more than that, there is a... every question leads to another question and another question and then 10 questions. And suddenly it's almost impossible to go into a learning session and come out with like less questions than you entered. Do you know what I'm trying to say? You come in with one question you want to answer and you leave with 10 more, right? And that happened today as well. And I'm happy that happened. So here's what I'm going to say. There is a VOD on YouTube right now available for anybody who wants to watch it. Please feel free to go to the comment section there and just type anything that you want to see more of from this stream. It could be more GPU stuff. It could be more Julia stuff. It could be more of any type of thing. On my end, I know I'm going to do the following because I'm still quite interested in analog quantum computation. I want to learn about the different types of quantum computers. I want to learn still what it means to be an analog quantum computer. I still don't know what that means. I want to learn, right? And so we'll go into this and we're going to learn about it together. And today was quite rambly. Some other days are going to be quite rambly, but hopefully as we start to really drill into the learning, it'll be a little bit less rambly, right? I only caught the final hour of the stream, but it was fun. The quantum world is really shaping up. Yeah, I'm quite interested to see where it goes. So let's talk about what happens from now. Like I said yesterday, I have signed some sort of goal. So Monday, Tuesday, Thursday, and Friday, my goal is to do some sort of research on stream, right? What this means is I want to do learning together streams. I want to do actually code development. I want to do stuff that's like actively either we're learning together or we're doing things together that are like progressing the boundary of human knowledge in some way. But Wednesdays are writing Wednesdays. I know it's not going to be everyone's cup of tea. I get that. It's kind of like just a separate day. Tomorrow is Wednesday. I thought about not doing a writing Wednesday. I used to do them a lot, but considering I'm just starting streaming again, maybe it's good to take a step back and really like have a couple good streams. But actually, I've got a really interesting thing I want to look into tomorrow. Sorry, I just hit the microphone. I have a really interesting thing I want to look into tomorrow, dealing with metrical foot analysis. So for those who don't know, metrical foot is a measurement of how people read poetry, for example. It basically, like if you were to read a poem like, I don't know, what's a good poem? Remember the 5th of December, right? Like the way you read is like, remember the 5th of November. It's November, not December. But point is, gosh, what a crappy thing to start with. But there's a way in which you read this, right? And you can clearly feel the feet, right? The reason this is quite interesting is because there isn't really a good way to analyze what the foot is in a poem. Like there are ways, but I'm curious to see if there's any like algorithmic approach or even machine learning model that could appropriately tell me where the feet are in a line of poetry, right? And more than that, I'm wondering if it's worthwhile, if you are writing poetry, to create a framework so that you can more easily tell people how to read the poem out. I did not remember at all. Actually, I've completely forgotten it. I'm so sorry. But anyway, my point is that like, I'm someone who loves poetry, and I want to spend a little bit of time thinking about how this works. And so tomorrow, again, we're not doing research, we're not doing quantum, we're not doing any of that kind of stuff. We're literally just going to take a step back, and I want to talk about poetry. And I'm going to talk about poetry for hours. People might not like it. That's okay. We're going to come back on Thursday, and we're going to do more research. Now, what research that is kind of up to you guys. I personally have clear things that I want to start focusing on. And so things that I want to do, for example, would be related to my animation engine project, GPU stuff, Julia GPU stuff, some molecular dynamics. I've got a lot of different things I could do. I haven't quite decided what I want to do for Thursday, but definitely tomorrow, taking a step back with poetry. I thought you were already done with the stream. Nope, I'm ending now. Thanks so much for stopping by. I think this is a good place to end. So I'm going to go ahead and paste all of this stuff here in the paper pile on Discord. Here we go, paste it here, Control V, enter, and I think that's it. So thank you guys. Next time you probably want to select live chat on YouTube. Be careful for next time. You probably want to select live chat on YouTube. Oh, that's a good point. You are totally right. Yep, my bad. Okay, anyway, thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. Please paste here. I don't have, yes. Wait, what do you want me to paste there, actually? I'll paste the Discord link really quick for everyone. Let me go ahead and do this. Create invite. Copy button. Should I edit this so it's... No, let's just do... That should be fine. Let's paste this here and paste this here. Enter and enter over here. Good. Okay, so that's it for now. Again, guys, thank you so much for coming in. If you liked this type of content and want to see more, just all I'm going to say is just stop by, hang out, chat. Again, I'm not going to say that these streams are like politically charged. They're not. It's just a stream about research. But I feel like as a person, the best thing I can do to just kind of be a good steward, like a good person in the world today, is just to share what I know and share what I can do. And And that's kind of what these streams are. They're just me trying to, I don't know, I guess make the world a better place by like one research question at a time. I don't really know what I'm trying to say, but my point is like, I had for a long time been a little bit afraid to do streams like this because I kind of felt like it's a little bit hard to be, I suppose, vulnerable in your learning process. I don't really know what the words are here. But I think it's really important to share the learning process with people because it is really enjoyable. And it is quite fun. And I'm hoping that through the process of sharing this with people and talking to people about it and explaining things together, we can learn and I don't know, maybe it turns into something. Anyway, thanks again, guys, for coming in. Again, have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Leos Labs. It'll be tomorrow. We'll talk about poetry. I'm excited to see you there.